this relation is not new. So there is no discovery here. This is just a relation that has been observed since the 80s. The first paper were using Einstein data, then Rosat data. So this is not something that, this was very well known and often used to better understand accretion properties in synergy with the X-ray corona. And indeed, this relation tells more about the physics, and this is just one slide to say that at the beginning, this relation was observed, and the main point why there is this tight correlation between the X-ray emission and the UV emission. If the UV emission is emitted from an accretion disk, the X-ray emission is emitted from a plasma of hot relativistic electrons that Compton up scatters the photons coming from the disk. So observationally, we see in the X-ray power loss, beautifully boring power loss, and in the UV, we see, again, power loss with emission lines superimposed. So these are the observational key point. But I'm not going to talk about the physics. I'm going to focus on cosmology this time. And this is just very briefly how the things works. So luminosity is, of course, has cosmology in it, so we can't use it to measure anything because it is cosmology assumed. So we go through fluxes. And I think it's now clear why gamma, there is no linear. So gamma different from 1 is key in order to measure luminosities, in order to measure distances, because otherwise just the technique doesn't work. So the FX, FUV relation, so the relation with fluxes is the way to measure independently quasar distances. And with this, we can then build a Hubble diagram. So the Hubble diagram is the relation between the distance modulus as a function of redshift. And this, so if you can see here, there are some pink points. These are type 1a supernovae, and you can really appreciate why there is some feedback here. And you can really appreciate how beautifully type 1a supernovae just go through the Hubble diagram with such a narrow scatter. Quasars, on one way, the scatter is high, much higher with respect to type 1a supernovae, is striking, but quasars very much extend the Hubble diagram to redshift that it would be unlikely to be probed by any type 1a supernovae. And I want to make this point because it's the complementary between these two techniques that makes all the machine like powerful in observational cosmology. So regarding the points, the colored points is a sample of quasars that we publish. It's our latest sample of quasars we published in 2020. These are 2,400 quasars selected mainly from Sloan and XMM Newton. That goes up to the highest redshift at the time. This is the redshift 7.5. And there are two key points here. So if we fit all the data below redshift 1.5 and we extrapolate the fit, which is a flat lambda CDM model with a dark matter equal to 0.3 to higher redshift, this is what you get. If you then fit all the data, type 1a supernovae plus quasars down to the highest redshift observable, then you get the red line. The black points that you see here are averages of the distance modulus in narrow redshift bands, which are shown here just to guide your eye. These are never used for fitting. There is a key point that I'm going to show you a little bit later. And what is key here, there is a deviation from the lambda CDM model, high redshift, with a statistical significance then, of course, is not that high, it's 3 to 4 sigma. But so if you talk to particle physics, they say, okay, it's below 5 sigma, non-existent. But we believe that we can actually detect this discrepancy a higher sigma, like even beyond redshift 6. So I can continue. So I want to quantify this first before I move on to the new results. So this is something that we did with Giada Barciacchi, who was a student of ours, and now she is a PhD student, Scuola Superiore Meridionale in Naples. So she published a suite of FETs with several cosmological models, and she, including also baryonic acoustic oscillations in the analysis, and she uses what is called the flat CPL model, but just without going into the technicalities, is an equation of state of dark energy that evolves with time. And the green point is the equivalent, it's not exactly, but is the equivalent of a flat lambda CDM model in the CPL, within the CPL. And the contours from supernovae plus quasars 1, 2, and 3 sigma are a 3 sigma deviation for the prediction of W0 minus 1, which is the standard for the lambda CDM cosmology. So this is the same here with omega mater and WA. So even though we detect this tension, if we want to interpret this tension physically, every interpretation that goes within a model, in this case, means that there is a evolving dark energy density with this value. It's called phantom behavior, and I'm not gonna talk about this anymore. So every time we make an interpretation, it goes within the model. But there is a discrepancy, and this is being seen with the data. So this is the key point. So I can continue to talk about the tension, but this is not exactly the point, because when we see a discrepancy with a flat lambda CDM model, the first thing that people will start to say, well, there is some bias in systematics. So all the rest of the work that we have been doing so far is to test systematics and bias in the sample. And this is my wish list, to be honest. So my wish list is I want to confirm the deviation with the highest statistical significance, but this goes hands in hands with testing any possible bias in systematics. And this is my wish square. So I want another group that confirm this deviation in a completely independent way. So the data are public, but please make your own quasar sample and try to fit it and see what you find. This is just a list of everything we have done so far. Some of this is not even submitted yet, and I'm gonna just go very quickly through it. So we try to understand whether there is a redshift evolution of the slope, for instance, as a function of redshift, test the sample selection. So I'm gonna go through a few of these tests that we made. And this is the first one, and I think this is reassure me every single time I see this plot, when I see that even though quasars are highly scattered with respect to type 1a supernovae, the average is a very good agreement with both type 1a supernovae in the common redshift range with type 1a supernovae. What about the redshift evolution of the slope? Well, we do every single time we have a new sample, we make this test, and we do not see any systematic or clear deviation with the slope of the relation as a function of redshift. So no redshift evolution of the slope. We do these every single time, but most tricky, is there any sample selection? And since the deviation is a high redshift, this is crucial to be done. So we test the sample selection at redshift higher than 2.5. We didn't find anything that is different from lower quasars, so lower analogs, lower redshift analogs of the quasars that we selected. So just power loss in the X-rays and very standard spectra, like in the optical. So we do not see anything different than the unobscured AGN analogs. The other criticism this is unpublished, we hope to publish this soon, is what if there is a differential reddening? So higher redshift quasar are more obscured in the UV with respect to the quasar at lower redshift, and therefore there is a differential gradient of absorption towards from lower to higher redshifts. So we test this, and we ask ourselves what is the color excess required, the dust rendering required in order to bring back all the data on average on top of the lambda CDM. So this is the question that we asked. And we find that at redshift, all the quasars that are beyond redshift 5, for instance, or redshift 3, should have a color excess which is higher, at least 0.1, or even higher, which is unphysical. So you should see the spectra that has been corrected by this color excess. The power law is completely unphysical, so we exclude this. We also check in a different way whether we do see any source of reddening, but we find it any, so the actual average reddening is lower than 0.02. So we exclude this, and we hope to submit this, all these tests that we have done soon. I'm not going to talk about this because I'm running out of time, but this is just to say that there is no host galaxy contamination at lower redshift, which is another contaminant in the optical. And regarding the future, well, Rosetta is now shut down, so there is no, and they are not going to turn it on soon as much as the war goes. But Rosetta would be ideal to test the technique at lower redshift, like below redshift 2. And Euclid is going to provide us with the spectra that we need a higher redshift. So about 30 quasars are expected to be observed beyond redshift 8. We'll see how it goes with Euclid. Euclid is fine, happily. So, and this is my take-home messages, and I'm going to leave you with this.
this work? Yes.
Okay, so now we have Silvia Onorato from University of Leiden, which will talk about proximity zone in quasars at redshift greater than 6.5 as a probe of supermassive black holes and the EGM in the epoch of ionization.
Thank you. Good morning, everyone. So, yeah, my name is Silvia Onorato, Ph.D. student at Leiden University. I work with John Nawi. And today we will see how we can use these proximity zones of high redshift quasars and how we can use them to study the reionization epoch. I will start with a bit of an introduction, since I think not all of you are familiar maybe with high redshift. And yes, starting with describing how the spectrum of a quasar look like through the different redshift. So here in the top and middle panel, we see some absorption feature that get more evident going at higher redshift. Is the so-called Lyman alpha forest that we know, I think, is basically a forest of absorption lines due to the presence of neutral hydrogen clouds at different redshift through the line of sight. And is an extremely useful feature that we can use to study the neutral hydrogen. But how can we study the neutral hydrogen when we go at redshift around 6? Since this Lyman alpha forest gets totally opaque because as a consequence of the cosmological density evolution of the universe. Indeed, here we see the so-called Gunn-Peterson throw, so it gets totally absorbed. So fortunately, there's still a way, and is in the spectrum of the quasar itself, and it's basically focusing in this part where there are other two useful features, the so-called damping wings and proximity zones. Then now I will describe a little bit more in detail. So what the damping wings are? As I say, they are a feature that is imprinted into quasar spectra, but is visible mostly at around redshift 7, because the requirement for that, to see them into the spectrum, is that we have a very high abundance of neutral hydrogen, let's say around 10 to the minus 1. So we have a mostly neutral universe. And they arise from the fact that the Lyman alpha is a resonance line. And so in presence of a very high fraction of neutral hydrogen, also the tails of the line are getting absorbed. So this is basically the effect that we see into the quasar spectrum. So since it's related to the presence of neutral hydrogen, we can use that to place constraints on the fractional neutral hydrogen. The other one is the proximity zone. So this is the effect that we see into the quasar spectrum. It's visible at redshift around 6. And in this case, we can say that the proximity zone is basically a region of enhanced ionization from the quasar, but now in an already ionized IGM. For the goal of my talk, I will focus a little bit more just on the proximity zones, saying now something else. So when we have a quasar, we need to take in mind there is a very powerful source emitting ionizing photons. So the radiation from the quasar is able basically to produce a kind of bubble of over-ionized AGM around the quasar itself. So the size of this bubble, described from this formula, depends on some characteristics of the quasar. For example, its luminosity, its lifetime, but also the fractional neutral hydrogen. Unfortunately, it's not directly measurable from the spectrum. So what do? We define the proximity zone. Is the region blueward of the Lyman alpha line, and we can use that as a proxy to study this bubble and place constraints on both the quasar lifetime and the fractional neutral hydrogen. Today, I will just focus on the quasar lifetime. And here I want to show you an animation that I hope, no, is not starting. How can I make animation to start? Maybe here, okay, yeah, it worked. So here we have a neutral universe, and we are keep increasing the quasar lifetime, and we see how the spectrum evolve. So when this time increase, we start to see this feature of the proximity zone. So what do we learn from this video? We learn that the two quantities, the RP and the quasar lifetime, are connected. So RP actually increases with increasing the quasar lifetime. But to be fair, the real scenario is more complex than this, because here we were assuming a neutral universe. So there are two different types of evolution, considering a neutral or ionized universe. But actually, at that redshift, the topology is patchy, so it's more complicated. But just for all my talk, let's just keep in mind that the two quantities are connected. And if one increases, also the other one increases. So what are the goals of my project? What do I want to do? What kind of science I want to do? So the idea is placing constraints on the evolution of the quasar, of the fractional neutral hydrogen during the epoch of reionization, placing constraints on the quasar lifetime, and then also study how the supermassive black hole growth at redshift higher than 6. Today, as I already said, we will just focus on this part. And to do so, I'm going to show you some proximity zone size measurement. Okay, let's start off with the data that I have. I have a sample of quasars. I have 45 quasars at redshift between 6.5 and 7.64. They are displayed here with M1450 as a fractional redshift. There are 10 BALs among them, all the data reduced using Pipit. There is a software developed by my supervisor and other collaborators. And they are pretty good spectra with medium-high spectral resolution. All of them are taken with these 3 main ground-based instruments complemented with some other. But the most interesting part of all of this is that soon they will be publicly available. So one will perform science with them. Why? Okay. Why is this sample so unique? So we already have proximity zone constraints. This is some literature, but as you can see from this plot, they are a lower redshift. So my sample is unique because I'm pushing at higher redshift at this limit. Okay, these are the main results I'm going to show you today. So let's start with a fancy image of my quasar spectra. Just this amazing image, rainbow colored, of 34 example spectra that I have. 7 of them need to be improved. Maybe I will add some other to the sample, but just enjoy the beauty of this plot. And if we want to have a better look on how one of them, for example, Pisco look like, it looks like this. This is an X-Sure spectrum. And as I said, we are targeting the proximity zone, and the proximity zone look like this. The second main results, actually the first science I've done with this data, is the composite spectrum. So maybe not all of you are familiar with what a composite spectrum is. So it's actually an average spectrum. I have a sample of data, a sample of quasar. I'm taking them and then creating a medium spectrum. So the steps to create that are just taking the spectra, moving them to the res frame, define a new wavelength grid that is defined here, then rebinning all of them since they're taken with different instruments, so they have different pixel scales. I'm using a unique one, and then normalizing the flux at a certain wavelength. So here I want to show you the difference that I get considering the total sample, so the 45 quasar, and then the sample but excluding the BILs. So I think I don't really need to convince you that there are not such big differences. So then for the rest of this discussion, I will consider the total sample. Here, if you're wondering, these are the number of spectra that are contributing to the composite for each wavelength, and the mean redshift that is contributing to the composite for each wavelength. Here, there's just comparison between my results, so including the BALs, as I said, with some other composites from the literature. There are not such big differences. In the inset panel, you will see the most interesting region for my purpose. Then also to improve the quality of the composite, I've applied some masks, masking for the telluric absorption, bad signal-to-noise ratio, bad sigma, removing outliers. So the conclusion of that is here we are seeing the average UV spectral properties of quasars at redshift higher then 6.5, and we notice that there's a consistent continuum slope between my composite and the others from literature that are also taken a different redshift. Maybe you will notice that there are some differences here, but the idea is that these differences probably arise from differences in luminosity between the quasars that we have used to create the composite. Let's move to the last results, maybe the most exciting one, but it's still preliminary. So we have proximity zone size measurement for 21 of the quasar in the sample. They are shown here, it's just overview. To make this kind of science, the first thing we needed to do was recreating the absorbed part of the quasar spectrum. To do so, we have used the principal component analysis. So fitting the red part, we have recreated the blue part, the absorbed one. And then we have used them to produce these results. The BALs for the moment are excluded, and then the idea is to extend the analysis to the full sample. I will focus on part of them just to have a deep look. So, as I said at the beginning, here we needed to use the definition of the proximity zone that is defined in Fan et al. 2006. So what a proximity zone is, how it's defined, is the region blueward of the Lyman alpha line until where the continuum normalized flux smoothed by a 20 angstrom boxcar filter into observed frame, so this red curve, first drops below the 10%. There's a yellow line, so where this red curve first drops below the yellow line for 3 consecutive pixels, we have the RP measurement. Here you will see that we have defined some errors. There's the error on the redshift due to the error on the Lyman alpha location due to the error on the redshift, the uncertainty on the continuum, and then we have our measurement. So for these 21 quasars, the measurements span between 0.23 and 6.19. This is actually a pretty small measurement, and this is this quasar here. So from this, there's the chance that this quasar is actually a young quasar at redshift 6.85. Let's just have a better look. So it looks like this, it's pretty small. And the spectrum, if you're wondering how its proximity zone is, looks like this. What do we know for the moment? Nothing yet. So further investigation required to assess what actually the quasar lifetime is. Okay, so just the last 2 slides to show a summary of this RP with other quantities. So here we have the spread of RP as a function of M1450, color-coded with the redshift for my data, being neutral and ionized IgM. So the idea is that the differences when the magnitude is the same maybe are due to differences in the quasar lifetime. So we need to figure out if it's that. And here we have the distribution of RP as a function of redshift, color-coded with M1415. So as I said, my measurements at a higher redshift compared to the literature. There are a couple that overlap with the Cindy's sample. There's a good agreement. So this is really exciting. But to be fair with you, there are measurements at higher redshift. The problem is that these measurements are quite different from mine. We need to figure out why. But we think that maybe it's due to data quality, because the spectral resolution of Mazzucchelli data is lower than mine. So let's see. I will leave you with my take-home message. So this is a summary of what I talked about. The idea is for future work to place constraints on the fractional neutral hydrogen supermassive black hole. And let's see. So thank you.
So good morning to
Sorry. Just wait. I know you're going to be late, but wait. So now we have Tommaso Zana from La Sapienza, University of Rome, and he will talk us about are there more galaxies that we see around high redshift quasars? You can go.
Thank you. Thank you very much. Good morning to everyone. I am Tommaso from Sapienza University. It is a pleasure to be here, and thank you very much to the organizer for the opportunity. So today I'd like to speak about the typical environment of a very powerful quasar at redshift around 6 or beyond. So I'd like to start from this beautiful artistic representation of an IGN, which I'm very proud of because I made it myself with artificial intelligence. Okay, and so we know that this kind of object, the most luminous of this kind at redshift 6, are likely powered from the accretion process of gas onto the most massive supermassive black holes with those masses. And so what do we know about their environment? So according to theoretical models, if we take this representation of cosmic web, this is dark matter, we would expect these most massive quasars to live within the most massive dark matter halo at that redshift. Most likely because you need to explain the steady gas inflows in order to explain those luminosities. But unfortunately, this has not been confirmed and validated by observations. It is very difficult to understand how massive is a dark matter halo, because dark matter, okay, you know it. And what can we do? We can count how many satellites we observe around them in order to probe the mass of the dark matter halo. So we can say there are a lot of satellites, a lot of companions. It means that they are living in a very massive dark matter halo. But as I said, there are a lot of papers which says that these quasars at redshift 6 and beyond live in overdensities, and also a lot of other papers saying the opposite. Because again, it is difficult to observe these sometimes faint galaxies at high redshift because of dust oscuration, absorption, and many other observational bias. Surely the best strategy to observe this object is through taking advantage of the C+ 158 micrometers, because it is not affected by dust attenuation, and but it is not affected by dust. And I guess almost all of them take advantage of this through the observation with the ALMA telescope. And I'd like to take a moment to use this paper by Venemans et al. As an example in order to understand what is going on. This is nowadays the most complete catalog of satellites around high redshift quasars. And here you can see the frequency of satellites. So they follow up 27 quasars at redshift 6 and beyond, and they observe many times nothing, no satellites. But sometimes they also observe 2 satellites or 3. So why it's so? A lot of the possibilities have been proposed. One of them is that it is a matter of feedback. So basically, the potential well would be there, but we wouldn't be able to observe them. We wouldn't be able to observe them because of powerful outflows, which would strip the gas, as it is exemplified in this rigorous animation. So this is a possibility. I investigated this through the use of cosmological numerical simulation. I already, this was my first work, so I'm gonna skip directly to the results. Basically what I did was analyzing 2 cosmological simulation, 2 in simulation with the very same initial condition, and only a difference in the prescription for supermassive black holes. And basically what I did was to identify different satellites. Then I developed a semi-analytical model in order to understand which is the total energy which was affecting, which was starting from the network of IGN, the accreting black holes in the simulation, and then hitting on the single target galaxy. This is the semi-analytical model, which depends on the accretion rate of the supermassive black holes, the virial radius of the target galaxy, obviously the distance of the galaxy. And so if you sum everything, then you have the total energy which is produced by the AGN and which is targeting the single galaxy. Here I'm showing you the results for 3 satellites. This is the energy. So, okay, so the energy is increasing from redshift 9 to redshift 6. And you can see that, for instance, this satellite, it is strongly influenced. This is like in between, and this is the least influenced satellite that I found in the cosmological volume. And here you can see, for instance, the effect on the star formation rate. So in the simulation with the AGN, the star formation rate is higher. This is the relative difference in order to better understand what is going on here. Which means that, no, it is not the feedback. So the feedback is positive. It is negligible on average, if you get the average of all the satellites. But you can find specific cases where the feedback is positive. Then we further investigated this through semi-analytical model. Specifically in this work with Ferrara, we modeled these quasars, a quasar host with an isothermal sphere, and in the very same moment, in the very same way, we also modeled this satellite with the very same, with another isothermal sphere and a disk which is perpendicular to it. And I'm showing you directly the result. So basically, here you have this parameter which depends on the dispersion velocity of the satellite with respect to the quasars. So this is basically, this depends on the mass. And this is the distance of the satellites over the radius of the satellite. So what it is saying that provided that the satellite is surviving to the outflow for a certain level of this eta parameter, which is almost always the masses that we are speaking about when we consider the satellites of high redshift quasars, the feedback is almost always positive. And so it is not the feedback. So many times, again, we know that sometimes satellites, there are a lot of satellites around quasars, sometimes we don't see anything, and it is not the feedback. So this is what we found, so it is positive. It has to be something else. Maybe it is a matter of an observational bias, which means that depending on the distribution of the satellite around the quasar, again, we are speaking about, we expect to have a lot of companions around quasars. Here I'm speaking about those massive enough to be observed, for instance, with ALMA. So here I'm speaking about ALMA, but this is true for every limited field of view instrument. What we're saying is that these cases are different. So if you have a limited field of view, maybe a part of the population of satellites is hidden. So we wanted to quantitatively investigate this aspect. And here you can see another scheme of how it works. Again, this is for ALMA, because we wanted to explain the results that I showed to you before. And the idea is that given the specific line of sight that you have, we can see more or less satellites. The idea is that let's try to make a rigorous framework in order to explain this distribution of companions. Ideally, what somebody would do is making a lot of cosmological simulation, cosmologically motivated, and every time to intersect the distribution of satellite with a random line of sight. And this approach is obviously undoable for computational reasons. So what we decided to do is to use Monte Carlo simulation every time to spawn random distribution of satellites and every time intersect them with some random line of sight. And specifically, we did the 10 to the 5th simulation with a variable number. So we spawn 1 satellite, 2 satellites, 3 satellites, and we were checking the response of this intersection with the line of sight of the telescope. How to generate satellites? We don't know, so we tried different models. We started with an homogeneous distribution, which means we just randomly generated satellites in the volume around the quasar. Then we try to refine a little bit the the gas using different radial law. The idea was to generate more satellite closer to the center with respect to the outskirt. So we use different models, which they are usually adopted in order to model bound systems. But here we just wanted to use radial laws in order to probe different distributions. So we use the Plummer profile, an Airquist profile, Navarro-Franken-White profile with different normalization constant, because the idea is that we want to every time spawn different number of satellites at the beginning in order to see how many we would observe. Then we use also a cross-correlation function, which is the same again. The normalization constant doesn't come from the validation from observation. This is a variable in our model. And our fiducial model comes from numerical simulation. Basically what we did, we tried to mimic the distribution of satellites, starting from a snapshot around redshift 6 out of 2 different cosmological simulations that are specifically made to describe those systems. And we centered on the central quasar, and then after using an halo finder, we mapped all the distribution of satellites, and every time we would have considered randomly 1, 2, 3, 4 in order to see what was going on. The power of this last model is that this is the only one who can describe the filamentary nature of what we would expect to be the distribution of dark matter around quasars. I'm going to show you the results. There are no results, and I don't know why. No, this is a problem, actually. Okay, the other one were beautiful, but let's forget about them. But let's focus on this, which is the fiducial model. Come on. So, so basically here you have the detected number of satellites with respect to what we are actually seeding. And here you can see that, for instance, if we get 1, 2, 3 satellites, if we seed 3 massive satellites that are always above the threshold of ALMA, at least 30% of the time, we wouldn't observe anything. So this is already a smoking gun of what is going on. So the observational bias can actually explain why many times, under the assumption that all the quasars live in the same environment, we wouldn't observe them. So let's try to put it in a more quantitative way. So this is like a likelihood. Then we wanted to add to this likelihood a Poissonian scatter in order to consider also cosmic variance, because we cannot say, okay, every time around quasars there are 3 satellites and this is the results. We also want to, it is better to say that that initial number of 3 satellites is instead the average of some Poissonian distribution. So we get a Poissonian scatter, we multiply it with the likelihood, and then we computed the posterior using this frequency from this data. This is the state-of-the-art data right now. So here, basically, we are saying how many satellites, on average, there are around quasars using current observation. And this is the result. Ah, thanks God. So let's not speak about the other models because I didn't show you the likelihood, but let's focus also for a reason of time around these models, the orange and the red one, which is our fiducial model, the one coming from cosmological simulation, because again, this is the more realistic model, the most realistic model that we used. So basically, we would expect, on average, around every quasars, depending on current observation, at least 2 satellites on average, which are massive enough to be observed. And this has numerous beautiful consequences. For instance, every time you observe a quasar and you don't know about the existence of any satellites around them, it means that they are there and you just have to increase the field of view, maybe using mosaic observation to observe them because they are there. So, okay, I will leave here with my conclusion. So we can actually explain this with an observational bias. We know that according to our fiducial models, we would expect an average of 2 satellites around each quasars. And also, this number 2 is perfectly in agreement with what we understood from cosmological simulation after radiative transfer calculation. So if we get the single case of the numerical simulation, we expect 2 satellites. Then when we generalize it in this way with the dark matter distribution of halos, we confirm this model. Thank you very much for the attention.
So now we have Alessia Tortosa from Osservatorio Astronomico di Rome, and she will talk about nuclear properties of Hyperion sample, connecting accretion disk winds and X-ray corona in the first quasars.
Thank you. Hello, everyone, and it's a very great pleasure to be here for the first time, even if I'm not that young. Yes, I'm gonna show you this result about actually the nuclear properties of the Hyperion sample, including also some other quasars. And the aim of this work is to see if there are connections between the X-ray parameters of characterizing the X-ray corona of these quasars and other parameters. First of all, this is supposed to work. What is the Hyperion sample? The Hyperion sample is a sample made by hyperluminous quasar at the epoch of reionization, and they are selected for having a huge seed mass. So and they also, of course, are also has the name say hyperluminous. So bolometric luminosity above 10 to the 47, and yes, so they have been selecting for having this seed black hole mass very high. So for having also a fast growth of this seed mass. So basically they are titans among quasars above redshift 6. These quasars are part of this XMM Newton heritage program, and the PI is Luca Zappacosta. Basically there are a lot of megaseconds of observations of these quasars. The quasars in total are 18, but 2 of them have literature have already been observed. So the heritage program is just for 16 quasars, and also there are not just the XMM observation, but an extensive follow-up in different wavelengths. I'm gonna focus on the X-ray data, of course. And as I said, the aim of this work is to see if there are correlation between coronal properties of these quasars and the velocity of the disk wind, but also with some physical properties of the quasar, such as the mass or the accretion rate, and evolution properties. So the seed black hole mass and also the redshift. As I said, I included the Hyperion sample, but I also included some quasars from other samples which show similar properties of the Hyperion sample. We put a threshold on the net count rate of the X-ray spectra. Also, we selected this quasar for having a measurement of the velocity shift of the carbon-4. So this huge table is to show you all the quasar of the sample. These are the Hyperion quasars, and these are the other quasars that we selected from Vito, Pons, and Connor. And this is just to underline that all the values are computed in a uniform way to be consistent. So all the black hole masses are computed with the same cosmology and the mass calibration, also the bolometric luminosity with the same bolometric correction, and also the seed black hole mass, which is computed with this formula, assuming an exponential growth from zeta 20 with a net into ratio 1, and with an efficiency of 0.1 and a duty cycle of 1. I want just to leave you this message. This is a mass, of course, but the information that it is giving us is not just the mass, because larger seed black hole mass or equivalent M seed means that these black holes had also an history of rapid growth. So it's not just an information of how it started, but also how it evolved. So another thing, all these quasars have measurement of the velocity shift of the carbon-4 that have been derived in an heterogeneous way, so with different methods. And we took into account all the different literature value in the analysis, making fits with the Monte Carlo simulation to basically to take into account all these values, both for the velocity shift and for the rest frame equivalent width. So results, finally. Oh no, almost. Also, the consistency was not just on the computation of the parameter, but of course also on the data reduction and analysis of the spectra. So we did the spectral fitting and the data reduction, following what Luca did showed in his paper. The spectral fitting is in the 03.7 kV band, which in rest frame is like from 2 to 50, 70 kV. So the model is very simple. It's composed by a power law with the galactic absorption, and basically we analyzed almost all the data of the Hyperion sample, so 2.3 megaseconds. And here I show you one spectra and the photon index versus the count rates. And so now, really the results. What we found is a tight and highly statistically significant correlation between the photon index of the primary power law and the velocity shift of the carbon-4. And also, as expected from the literature, a relation between the equivalent width of the carbon-4 and the velocity shift of the carbon-4. What does it mean? So the power law, the photon index of the power law is giving us an information about the steepness of the spectrum. But of course, the steepness of the spectrum can be related also to other parameters, such as the cutoff. So we also checked the values of the cutoff for these sources, and so we find very low values for the high energy cutoff, meaning that the corona is pretty cold. And but the correlation is not as tight and statistically significant as the one with the photon index. Maybe because we cannot constrain all the values of the cutoff. As you can see here, there are a lot of lower limits. What does it mean? So there can be two interpretations that actually are not they do not exclude one the other. So basically, if we consider that these sources are accreting very fast, have been accreting very fast, we can take into account that there is the presence of winds and outflow, and that are also traced by the velocity shift of the carbon-4. So if there is a high mass outflow rate, the disk wind can deplete the matter from the accretion disk that result to be truncated. So basically the corona is irradiated by UV photons that are softer, let's say. So the corona can be cooler and the spectrum can be steeper. But if we consider this in the scenario of super-Eddington accretion, basically the difference between sources accreting in the sub-Eddington regime and in the super-Eddington regime is the accretion disk. In the sub-Eddington regime, the accretion disk is the standard Shakura-Tsunaev accretion disk, and there is the corona is fed by evaporation from this accretion disk, but this is a limited process, so the corona cannot be that thick, while in super-Eddington accretion, the disk is slim, so geometrically thick, and there are also a lot of winds that can feed the corona, so the corona can be very thick and can generate, so it can be also very cool. Another things to explain the other result, the correlation between the equivalent width and the velocity shift 4, which is something that we know from the literature. This is something related to the line profile. We know that the line profile is composed by a narrow component, the virialized component, and a broader component related to outflow. So basically, for highest velocity, the virialized component is lower, so the line is broader, and for lower velocity, is the opposite. Another interesting result, we checked correlation between the photon index and the Eddington ratio in these sources, but we cannot find a real good correlation, even if we know that in the literature for different samples of AGN, not only quasars, there is this relation, but the point is that here we are looking at a very narrow range of Eddington ratio, and also we are not sure that these values of the photon index are that high, because we are not taking into account the cutoff, but we cannot disentangle between these two parameters in this kind of spectra. And we checked also the correlation between the alpha X and the velocity shift of the carbon-4, since we know from Luca's work that he did on the WISH quasars that there was this relation, but again, we cannot find any relation in between these two parameters. So, last thing that we check is if there is a relation between the photon index and the seed mass and with the redshift. So we find both a relation in both cases. We tend to exclude that there is a relation between the photon index and the redshift, also because the time range is very small, so there are no reason for being evolutionary differences in something like 0.2 gigayears. So maybe there can be a relation between the photon index and the seed mass, also because the seed mass is telling us something about the accretion of these sources. So highest masses and means that these sources have accreting more, so more they are more, let's say, super Eddington, there are more outflows and winds, so the spectrum can be steeper because the corona can be cooler. To test this, Luca made a proposal, submitted an XMM large program to increase the range of the seed black hole mass. So let's see if we can strike the relation between the photon index and the mass, and I leave you my conclusion here, and thank you for your attention.
Thank you very much. Okay, we can start again after the nice break. And now we have Yeronshu from Unipa Palermo here, so that we talk about ultra-fast outflows responses in high accreting supermassive black holes.
Okay, thank you. Hello everyone, good morning. I'm Yeronshu, a PhD student from here, INAF, Palermo and University of Palermo. Today I will talk about ultra-fast outflow responses in highly accreting supermassive black holes. But I need to mention my talk is mainly focused on the nearby agents. I don't know why the organizers put my talk in this session, and the address are all relative to the high redshift quasars. Okay, so as we all know, agent is a system powered by the accretion onto a supermassive black hole. Besides accretion, agent could also eject outflows into the surrounding medium and release energy in the form of radiation, jets, and winds. Here is a schematic plot including all kinds of agent winds. And through the X-ray observations, we could probe the very inner region of these agent systems. So we could observe the warm absorbers and ultra-fast outflow, named as a UFO, in the X-ray band. And I'm particularly interested in UFOs because, as their name says, it has an ultra-fast velocity and is usually highly ionized. So such kind of outflows could carry up a huge amount of kinetic energy, which might be sufficient to affect the evolution of the whole galaxy. It's a very promising candidate to drive the agent feedback, which could quench the star formation rate of the whole galaxy and affect the growth of the supermassive black holes. However, due to the limitations of the current facilities, we cannot directly see the UFOs around the supermassive black holes, but we could detect them in the spectrum. UFOs are usually detected with a strongly blue-shifted absorption feature in the X-ray spectrum. And here is a typical X-ray spectrum of a quasar, PDS 456, and the absorption feature comes from the outflowing gas in our light side, while the emission component results from the plasma mixed sunlight with our light side. In the past 2 decades, scientists have already observed a large number of UFOs in agents. However, their underlying driven mechanism is still not quite clear. One popular theory is the radiation-driven outflow, where the winds are accelerated by the strong radiation pressure, so it's natural to expect this kind of outflow in the highly accreting systems. So like the upper right simulation shows, UFOs could indeed exist in high attendance agent and tend to be the equatorial direction. And the other popular theory is magnetically driven outflow, where the wind is accelerated and launched along the magnetic field lines, like the bottom right MHD simulation shows, tend to be the polar direction. Since today I will talk about UFOs in highly accreting systems, so you could expect me to put more emphasis on the first explanation. There are 2 pieces of evidence for the radiation-driven outflow. The first one was observed in a narrow-line Swift-1 galaxy, which is R13224, while the equivalence width and the flux of the absorption iron 25 or 26 ion transitions decreases with the X-ray flux, like the left plot shows. It was explained by the gradually over-ionized plasma in the strong radiation field. The other evidence was observed in both R13224 and PDS 456. Like the right plot shows, the blue shift of the UFO absorption feature increases with the flux. So if we plot the UFO velocity versus X-ray luminosity, we could find the positive correlation between these 2 quantities. Since these 2 systems are high accretion agents, so it suggests the UFO is accelerated by the strong radiation field in highly accreting systems. However, this statement is only made from only 2 cases. Then I will introduce a peculiar case from my work, which is YAGN0707. date back to my first PhD project. The left plot shows the evolution of the UFO properties versus X-ray flux. We could find the UFO column density, ionization state are correlated, while the UFO velocity is anti-correlated with the X-ray flux. The last panel is interesting because it's opposite to the trend we observed in the previous two cases. We explored several possibilities, but here I will just show our favorite explanation. YAGN0707 was once estimated to have an extremely high attendance ratio, so it's definitely a super attendance source. The strong radiation field could modify the inner structure of the accretion disk, like the right schematic shows. It could lead to a slim inner accretion disk. And when the source becomes brighter, the wind launching radius could be extended outwards, yielding a slower UFO velocity, and reproduce the observed anti-correlation between the UFO velocity and the radiation luminosity. So based on the results of YAGN0707 and in the previous two cases, we can just naively say that the UFO launching mechanism in high accretion systems are likely driven by the radiation pressure, but it's more complex than we thought. We need a population study to provide a comprehensive understanding for the UFO launching mechanisms. So before I show the results of my sample study, I would like to mention several sample selection criteria. We explored all the archival XM Newton data sets and put more emphasis on the high resolution RGS spectrum and pick up several suitable targets. The first criterion is that we only consider the type 1 agent because we don't want the high resolution RGS spectrum, which covers only the soft X-ray band, to be significantly affected by the heavy obscuration. So then the second criterion is that to investigate the UFO response to the source variation, we need enough statistics. It requires either we have a very long exposure time on the source, or the source is intrinsically bright enough. The last selection criterion is that also is the most important requirement is that they should have the UFO in their spectrum. Otherwise, we cannot study anything. So we manually set the detection threshold at data C-sex larger than 30, which corresponding to 4.6 sigma significance in the stacked time average spectrum of for each target. Then I will show the result of a benchmarked target in my sample, which is Markelian 1044. At first, I model the broadband spectrum with a continuum model consisting of componentization, soft access, which is commonly observed in AGN, and relativistic reflection components to extend the spectrum, like the blue dashed line shows in the left plot. And when we look at the residuals in the second panel, we could find strong residuals around 1 keV, emission residuals around 1 keV, and absorption features around 1.2 keV. So we have to include an additional photonization, emission, and absorption component to explain these residuals. However, to confirm that our photonization solution is a globally best fit solution, so we then perform the grid search of the photonization model for the time average spectrum. And here I just show the scan results for the absorption component. We can find the UFO is strongly detected with a high ionization state around log psi equal to 0.4, which and the velocity is ultra fast velocity around 0.13 speed of light, with also a very strong detection significance. So after confirming, by the way, this method is very powerful because it could locate the global best fit solution and also identify any potential multi-phase nature of the outflows. And so after confirming the UFO detection in this source, then I perform the flux resolve the spectroscopy. The left plot is Gaussian line scan results over the flux resolved spectrum. from the low to high flux levels, you can see that the blue shift of the absorption feature increases with the X-ray flux. Like the right plot shows, it has a positive correlation between these two quantities. So it suggests UFO in Magellan 1044 is accelerated by the radiation pressure. Then I collect the results of the remaining targets. In my sample, we only have totally 7 targets. Here are the rest 6. Here I just show the UFO velocity versus X-ray luminosity. And one important discovery is that we find the previously undetected UFOs in 2 agents, which are IJ1034 and PG1244, thanks to our powerful gray search method. And also with large academic Newton campaign sources, we could detect the UFO with strong significance in all of these sources. And when we look at this plot, we find the UFOs in our sample are either likely accelerated by the radiation pressure, which shows a positive correlation, or remain unchanged, probably due to some time delay of the momentum response to the source variation. If we fit these points with a linear function in a logarithmic space, then we compile the fitted slopes with the attendant ratio. We find an interesting behavior. We find that in general, the fitted slope corresponding to the radiation acceleration decreases with the attendant ratio. How can we explain this? In the standard accretion, standard thin disk accretion scenario, we would expect UFO acceleration would be stronger when the source becomes brighter. However, in the high attendant regime, the situation changes. We consider 2 possibilities. The first one is, as I mentioned for the case of 1H0707, that the strong radiation field could change the inner geometry of the accretion disk and extend the wind launching radius outwards, yielding the slow velocities. And then another possibility is that in a strong radiation field, we would expect the plasma is over-ionized, which means it will experience the lower radiation force, so which could also reduce the radiation acceleration. So we think the combination of these 2 mechanisms could explain this anti-correlation, observed anti-correlation. Then the last slide before the conclusion, I want to emphasize how important the future missions, like Prism, although it's recently launched, and the new Athena, Lemma, or Arcus could help us to reveal the UFO launcher mechanisms. First of all, with the unprecedented spectrum resolution, here we could distinguish the launching mechanism directly through the UFO absorption line profiles. Here is a plot, the theoretical prediction from different driven mechanisms, and shows the corresponding line profiles. You can find radiation driven here marked as line driven. The blue lines, it has an extended red wings in the line profile, while the magnetically driven outflow has an extended red, maybe I say something wrong. The magnetic driven outflow has an extended blue wings in the line profile. And so that's one of the improvement from the future missions. And the other point is that with a large effective area, it will enable the on-time spectrum modeling for the UFOs without the need for smoothing the wind features, which is required by the flux result of the spectroscopy. Here is new Athena XI field simulation for the UFO response in PG1211 with only 10 kiloseconds exposure time at different from low to high flux levels. We could trace the evolution of UFO properties such as UFO velocity, like the blue shift shows in these plots, and also the UFO ionization states and the column density at different changes when the source luminosity varies. So we can use this to reveal the UFO launching mechanisms and justify or reject my discovery of this work. So that's all. The takeaway message of my work of my talk is that UFO in high accretion agent are likely driven by the radiation pressure, but the acceleration may decrease when the source when the accretion rate increases. Thank you. That's all.
Thank you very much.
Sorry.
Okay. Okay, now we have Lea Marcotulli from Yale University, and she will describe us the most powerful persistent jets through cosmic time. So.
Thank you. So yes, hi everyone. My name is Lea Marcotulli. I'm also an Einstein Fellow at Yale University, and I would like to point this out only because I know there is a few young people in the audience. So if you're curious about the fellowship, how to apply for it, and what goes into it, come talk to me at lunch. I'm here to listen to your research proposals. And also, I am the person that is going to give the summary observational talk this afternoon. So if you have not sent me the slides and you're presenting some observational results, please send me the slides, and I will try my best to summarize quickly what we talked about in this meeting. All right, so let's talk about some kind of AGNs that have not been covered yet in this conference, which is the blazar jets. So blazars are these powerful jets powered by a supermassive black hole that's rapidly accreting matter for its surroundings. And when they're pointed very close to our line of sight, they're called blazars. And probably many of you are very familiar with these kind of plots, but I would like to go through it just 1 second so everybody's in the same page. So what we are seeing here is several spectral energy distribution of blazars that, as you can see, have this peculiar double hump shape that extends from radio up to gamma rays. So multi-band emitters, extremely variable sources. And when people looked at them as a population, they realized that there was sort of a sequence that these sources were following based on their luminosity. So they took a sample of gamma ray detected blazars. This is work from Ghisellini et al. In 2017. And as you see that the low luminosity sources have the peak of their spectral energy distribution at very high frequencies. But as we go to higher and higher luminosities, both of these peaks shift towards lower frequency, to a point where actually the most luminous of the class peak in the MEV band, and therefore we call them MEV blazars. Now these sources are the most powerful persistent objects that we know of in the universe. They can reach bolometric luminosities up to the 10 to the 48 or 10 to the 49 ergs per second, and they're so powerful, we are also detecting them at the highest redshifts, even beyond redshift 6. So extremely early on, at a point in time when the universe was barely 1 to 2 billion years old, here you see a statistics map of the furthest gamma ray detected blazars, a redshift 4.3, but with X-ray telescopes we went even further. So really powerful, really earlier on in the universe. And it appears that there is, as we go higher and higher in redshift, the black hole mass of these sources increases. So here you see a histogram of blazars detected below redshift 3 in blue and blazars detected above redshift 3. This is the histogram of the black hole masses, and as you see by eye, the red histogram peaks toward higher mass black holes. So as we find more and more sources at this high redshift with such high black hole mass, comes the question as how did this black hole grow so big, so fast, and what is the connection to the jets of the AGN? So to understand this kind of, to answer these kind of questions, what we can do is, first of all, we keep finding more of these objects, but also we need to understand how they evolve through time. And when we talk about the evolution of the blazar class, we usually consider 3 scenarios. One, it's a pure density evolution. So as we go through time, the number density of sources increases or decreases, but the luminosity is on average the same. Or maybe we see a luminosity evolution. So number densities are more or less constant through cosmic time, but the luminosities of the sources may be higher or lower. Or maybe the scenario is a bit more complex, so we have a mix of these 2 cases. However, once we know the number of sources at high redshifts and we can understand their evolution, and we know their black hole masses, we can encapsulate all this information in the so-called supermassive black hole space density. Shown here from the work of Sbarrato et al. In 2015, here is supermassive black hole space density of black hole masses greater than 10 to the 9 solar masses as function of redshift. What the author found in this work is that there was a dichotomy between radio-quiet AGN, traced by the blue line right here, and radio-light one, traced by the orange line. Now, the radio-quiet AGNs are the ones that don't have strong radio emissions, so don't have strong jets from them. And as you see in their density, they peak around redshift 2, which is the so-called cosmic noon, where most sources that we know of in the universe peak at. While if we look at the radio-loud ones, which are traced by blazar sources, we see that their peak in evolution is quite earlier on, at a redshift about 4. So this, again, hints to the fact that could be a connection between a fast black hole growth of the AGN and the presence of a jet. And for these kind of studies, of course, they strongly rely on number of sources that we found per redshift bin. And why do we rely on blazars? Because when we detect a blazar source, we are really lucky in the sense that we are really looking down the barrel of a jet. And by detecting one source, you can actually infer the size of the population. So how many jets are there at the same redshift with the same black hole mass, but they point away from us so we don't see them. And this is so-called 2 gamma square correction. Now, there are some correction to this correction, but in general, if gamma factors, those are the bulk Lorentz factor of the jet, so how fast are your particles moving through these magnetic field lines, and they're of the order of about 10 to 15. So for every blazar you see, you can infer the presence of 200 to 400 such sources, okay? So this is why we want to go to the high redshift universe using blazar sources. And another thing that some of you may be interested in is how much blazar contribute to the so-called cosmic high energy background, which is shown here in its intensity as function of energy. This is the integrated emission of all the sources in the universe, resolved and unresolved, that emit from soft X-rays up to gamma rays. And blazars have been understood to produce different percentages of this plot. So if we zoom into the gamma ray part of things, as detected by the Fermi LAT, this is the so-called total extragalactic gamma ray background, or EGB. Data points that you see here are the ones detected by the instrument, and the gray shaded line is the one, how much blazars are contributing to this plot. So they can contribute about 30% below 100 GeV, and as we go to higher and higher energies, they contribute more and more. In the X-ray part of things, here is a zoomed-in version of the cosmic X-ray background. Many of you work with AGN that emit X-rays, so you know that this background is actually produced mostly by normal AGNs without jets. But if we zoom into higher X-ray energy, so above 14 keV, blazars start to contribute about 5 to 10%, and the same one that produced this little of the SCXB can actually have been predicted to produce 100% of the MEV background, which is the mid part of this plot, which is yet to be explored by another OSCA mission, so these were data points from the 2000s, okay? But we don't have a new MEV mission, and we can rely on X-ray and gamma rays to understand what blazars do to these kind of plots. So, to understand and answer some of these questions, again, we need to understand how the source class evolves. And let me tell you a little bit about the evolution of MEV blazars. Now, to derive any evolution function, what you need to do is produce a luminosity function study, which is telling you the number of sources per luminosity bin per co-moving volume, so you can find these sources through time, okay? Talking about MEV blazars, the one that peak in the MEV band, we don't have an all-sky MEV mission that we can use, so we rely on X-rays. So in this case, we wanted to create our sample of blazar sources, which is from the Swift BAT telescopes, so hard X-ray telescopes that had measured redshift and fluxes. And then so here is the whole sky map of the BAT survey. In the gray data that you see here is all the sources detected by the BAT, and in red are our blazar sources. 10% of the catalog, not a lot of sources, but enough to do our studies. Farthest redshift at 4.6, so really we have a huge coverage in redshift. Then we performed a set of cuts to minimize some uncertainties on the fact, for example, we cut out the galactic plane to avoid source confusion, and also we select only the sources detected above signal to noise of 5. So significant sources, this is about 120 sources. And then we need to remember that every survey has its biases. And in the case of the BAT, 105 months, this is due by the exposure of the instrument. So here you see the exposure map of the BAT 105 month catalog, and you see that the lighter areas are the ones that have been exposed for longest, the grayish ones for shorter. So if you look at a point in the sky for longer, you're gonna go deeper in sensitivity, shorter, you're gonna see fewer faint sources. So you take this information and you produce a so-called sky coverage of the instrument. This is shown as function of flux, and you can think of this as a probability as function of flux, that your instrument will detect sources above a flux threshold, above a significant threshold, somewhere in the sky. So at high fluxes, this probability will be 1, and then as we go to lower and lower fluxes, you see it drop significantly to the point that for every source we detect at the limiting flux of 5e to the minus 12 in this case, we actually need to correct for it the fact that we are missing about 200 such sources, not because they're not there, it's just your instrument cannot see them, okay? So you have your catalog, you have your biases. The last thing you need is a bunch of X-ray luminosity functions to explain the evolution of these blazars. Without going too much into the details of how to derive the luminosity functions, here I present to you the most up-to-date X-ray luminosity function of MEV blazars. To the left, you see it as function of redshift, to the right as function of luminosity. And I would like you to take home 3 main points from here. First of all is that we confirm that these sources evolve positively, so there are more luminous sources as we go through cosmic time. The best fit to these luminosity functions show that the evolutionary peak is at redshift 4.3. Now, this representation doesn't really show this turnover right here. It's just a representation issue, let's say. But best fit shows that the redshift is at 4.3. So really, we confirm that these sources are peaking that earlier on in the history of time, again, connected to the supermassive black hole space density. But if we look to the right, as function of luminosity, no matter the redshift bin that you look at, you see that we are sampling a straightforward power law. This is telling us that we cannot yet tell apart whether a density or a luminosity evolution is taking place in the source class, because they're equivalent to each other in this representation. You can move this power law up and down, left and right. We don't really know what is happening. What we will really need is to see a turnover at every redshift that we could follow through redshift bins, and so we could understand the evolution. You see it maybe here a little bit, but within statistical uncertainty, this is not very clear. Once we have these models, we can understand now the contribution of blazars to the X-ray background and the MEV background. So here is X-ray plus MEV background. X-ray part of things, blue you see the density evolution prediction, pink the luminosity evolution prediction. And you see how in X-rays, they can account for 2 to 10%, but they can account up to 70 to 100% of the whole MEV background. So major contributors. We also know that other source classes can make up a little bit of the MEV background, so maybe the luminosity function is a bit better describing the source class. In terms of number densities, we realized that overplotting it with the work of Aiello et al. In 2009, number densities at higher redshifts are a bit lower than previously detected, so about a factor of 2 or 3 at redshift 4. And within this population study, we could also understand the distribution of gamma factors, which is important for the 2 gamma square correction. Turns out, average are about 8 at most 10. So this implies that when you put it into the context of supermassive black hole space density, you have lower number density and lower gamma factors that usually people assume a gamma of 15 when they do these corrections, but maybe it's a bit lower. So at the end, this peak maybe is still there, but it could be a bit lower. We just need to redo these kind of studies. And finally, we wanted to emphasize prediction for new upcoming MEV missions. So because these sources will peak in the MEV band, how many of them will be detected by an upcoming MEV mission if we had one? So you can produce a number count versus flux kind of plot for different MEV bands. And here you pick your favorite instrument, draw a straight line with the sensitivity that it will have in the years that it will be operational. And here we tell you the number of sources that it would find. And I would like to highlight that COSY will fly in 2027 and has some capabilities of discovery. 40 MEV blazars detected at the peak, so we really would classify them right away as MEV blazars. And then, of course, we would need bigger missions, Amigo, Amigo X, Astrogan, but those will be proposed to new NASA or ESA calls. And we also have some sensitivity with the Fermi LAT in the MEV band. If you're curious about this, ask me about it. I have something to tell you. And finally, my last slide. We could also make some prediction for neutrino detections. MEV blazars could make some neutrinos. And so we said, okay, if COSY were to fly, how many coincident neutrinos would we find? Given a lot of assumptions behind this, so take these numbers with a lot of grain of salt. But it turns out that COSY could detect up to 2 neutrino events, and more sensitive mission could detect even more. This is with IceCube prediction. So I'm gonna leave it here because I'm running out of time, and thank you for your attention.
Thank you very much. Some question?
Basic question, actually. How is the redshift determined for these sources?
Through
Because
spectroscopy.
yes, but for Blazar, as far as I remember, lines are extremely weak, right? So
Okay, so now we have Elena Bertola from University of Bologna and Observatory of Arcetri, I don't know where. And she will tell us about the X-ray corona of high luminosity AGN, the case of that telephone number that I'm not trying to pronounce.
It's fine, I'm going to say that. So, hello everyone. The reason why there's all of these affiliations here is that I carried out this work while I was doing my PhD, which was in Bologna, with these other full list of people that helped me through, and now I'm a postdoc at Arcetri since May, so this is also why there's all of the logos up there. So the point of my talk today is to tell you about the properties of X-ray coronae in high luminosity AGN, and I'm going to focus on APM-Y279. First, we already saw this in Alessio's talk, but basically, and other talks before, basically just a quick sketch of what we see in the X-rays when we're talking about AGN. So we have the black hole, the accretion disk, and the X-ray corona, and basically what's happening is that the UV disks, UV photon disks are upscattered by the corona, and they become the X-ray emission that we observe, but then this X-ray emission, it partly comes straight to us and partly goes back to the disk or to other clouds and then gets reflected. And here is a typical, let's say, X-ray spectrum of an AGN, where we have the primary emission produced by the X-ray corona itself. Then we have the reflecting continuum with the fluorescent lines. These are the iron K alpha and iron K beta, and the reflection bump. And also we can have absorption at the soft X-rays. And one parameter I will use later on is the reflection fraction, which basically is a measure of how much reflected emission we are seeing compared to the intrinsic emission. It's usually given as the relative fraction of a reflected emission that is expected from a slab that is subtending a 2 pi solid angle. There are two parameters that can be used to describe the properties of the corona, and these two parameters are the compactness and the temperature. They are both unitless parameters. In fact, the compactness depends on the size of the corona and the luminosity of the corona, while the temperature basically is just a weird way to write the electron temperature, so to get rid of the measuring units. Basically, what we see from how the compactness is defined is that if the compactness is higher than 1, then so if the luminosity basically is higher, then the ratio of luminosity and size is higher than 1, a particle loses a significant fraction of its energy going through the X-ray corona or the system. While if the temperature exceeds twice the rest mass of an electron, then 1 MeV, the photon-photon collisions become, the photon-photon collisions happen between hard X-rays, and they create positive neutron and positron pairs. So the corona, and then there was this guy, APM-Y279, which is a very particular one, so is the one that I'm going to present to you today. So this is the spectrum of APM-Y279 in 2019. We can see that there's neutral absorption in the soft band. Then we have a very prominent iron K alpha line, a Compton hump, and also we can see the descent toward the cutoff. However, APM-Y279 is an AGN that is very well known in the, let's say, high redshift X-ray community, and this is because it's the archetype for high redshift ultrafast outflows. It was the first quasar, a redshift above 1 or something like that, to show ultrafast outflows already in 2002. And one of the peculiarities of this source is that it always showed the double velocity component in its UFOs, and also they were extra fast, reaching velocities that are as high as 0.6 C. And also, it's extremely bright, and this is because it's gravitationally lensed. And our 2019 data, completely different. We don't see UFOs, the flux has dropped by almost a factor of 2, and we see this very, very strong reflection continuum. And if you remember what I showed you before, this is very strong compared to what we are expecting. In fact, the reflection fraction here is 2.8. And by its definition, the reflection fraction is lower than 2. So here is there's going on something that it's physical, basically. And to explain this, we took all of the X-ray observations that were available for APM from 2000 up to our 2019 observation. And we investigated the X-ray flux, the reflection flux, and the reflection fraction. So basically, what we see is that if we focus on the trends, is that the total hard band X-ray flux of the source was constant and then dropped between 2008 and 2019, while the isolated reflection flux has kept constant throughout the years, and the reflection fraction shows a steep increase corresponding to the steep decrease of the total flux. So our interpretation here is that the reflection component that we see in 2019 data was already in place before, but it was completely buried in the very strong intrinsic emission of APM, and the reflector is far enough not to have felt the difference in the intrinsic emission. Sorry. Then we wanted to place APM in the context of the coronae of AGN at all redshifts. So this is, as I showed you before, the situation before 2019, so before our NUSTAR programs. And here is the situation now. So here we have updated also the lower redshift measurements with all of the works that came out after 2018. And here you can see our high redshift points. These are the two published in Lanzuis in 2019, and this is APM Y279. As you can see, our error bars are extra big, but that's because of the quality of the data. And here, what you can see is that all of them fall in the allowed region of the X-ray luminosity high energy cutoff plane. And one thing that is worth mentioning here is that each threshold line corresponds to a different black hole mass. So the solid one is 10 to the 8 masses, then we have the dashed one, and then we have the dashed dotted. And the two colors for 10 to the 8, 10 to the 9, and 10 to the 10. And then the two colors correspond to two different geometries for the corona. One is slab and the other one is hemisphere. So when comparing these points with the thresholds, one has to check for the right black hole mass. And our AGN here are all more massive than 10 to the 9, or near 10 to the 10. APM is actually 10 to the 10, so they all fall in their allowed region. And then after this work, there's been more updates, especially these three works. One is Marinucci 2022, which is low redshift AGN, but very luminous, and here is only a lower limit, however, but can be consistent with the compactness temperature diagram limit. And then we have this point by Camun 2023, which is a very cool corona at redshift below 1. And then we have the results, the preliminary results by Zappacosta et al. In 2023 on the Hyperion sample, and this is the case in which the gamma is set to a reasonable value, so 1.9. Then what's next, basically? So we only have 3 points here, so anything can be happening, right? So what we want to do is to increase our sampling of the high luminosity and high redshift range. And to do this, we went back to all of our catalogs on how we selected the first AGN for cycle 3 and cycle 4. And so basically by cross-matching the Chandra source catalog and the XMM catalog with the SCSS data release 16, we selected all those AGN that are basically radio quiet. So we made sure that we took away blazars and blazer candidates because they could contaminate our X-ray emission, and also we wanted only radio quiet AGN, so to get rid of jets. And this led to the selection of another 10 or maybe 12, I'm not so sure, high redshift AGN that are radio quiet and are also bright enough to be observed with Nuster, which is not trivial. And of these high redshift AGN, 2 were already in our previous cycles. So basically we were left with the remaining 8. And as you can see, the redshift range goes basically from 1.3 up to 2 something. So we're sampling a lower redshift range than before, and their luminosity basically cover the pink area over here. And so far, we got 2 observations. One was not bright enough, too sad. And the other one is this guy here, which falls precisely where we were expecting him. So now we are very excited to see the rest of the data and keep populating this plot. And I don't have my summary slide was canceled just like my flight today. So I'll stop here. Thank you.
Okay, so the first one is Alessandro Trinca from Osservatorio Astronomico in Rome, and he will tell us about light from the cosmic dawn, the origin and observational signatures of the first black holes.
Thank you. Hi everyone, I'm Alessandro, a postdoc at the Observatory of Rome, and today I'm going to give you a very brief overview of the work that I've been doing in collaboration with a lot of people on trying to investigate the nature and the origin of the first accreting black holes in our universe. Now, since its launch, JWST already started to improve deeply our knowledge of the population of high accreting black holes at high redshift, with more than 40 detection of faint AGNs, which extended the current AGN frontier way deeper, both in redshift, with detection of candidates up to redshift 11, but also downward in terms of black hole mass, starting to probe the regimes of potentially heavy black hole seeds. And these systems, as you can see, are also quite overmassive in terms of black hole mass, and this, of course, might be a potential observational bias, but this is telling us that they grew up very efficiently at early times, so they're very promising to explore the early build-up of supermassive black holes. And we want to explore this complex scenario with the Cosmic Archaeology tool, which is a semi-analytical model designed to explore the early coevolution between supermassive black holes and host galaxies, and it is characterized by a very detailed seeding prescription for the first black hole seeds, and can provide catalogs, large statistical samples of AGNs and galaxies, assuming different scenarios for the black hole seeding and accretion. And just to give you an example of the prediction of the model, here I'm showing you the UV luminosity function at redshift 5, and as you can see, the black points are very consistent both in the bright end of the AGN luminosity function, but also turn out to be in a good accordance with the unusually high number density of faint objects that has been found by recent JWST detections. And before the first JWST data came out, we actually wanted to do some prediction of the expected number of accreting black holes observable with different JWST surveys as a function of different redshift range and luminosities, and for the observable population of systems to make a statistical investigation of the ranges of black hole mass, metallicity, and stellar mass that we should observe. And for what concerns the typical black hole mass, we see that we found that a higher redshift, if we will be able to observe something, we preferentially, the field of view of this survey preferentially selects smaller black holes with mass around 10 to the 6 or even below. And these predictions have actually been confirmed from the detection of the first redshift higher than 8 black hole candidates, respectively redshift 8.7 and 10.6. And these are extremely interesting systems because actually they can tell us something on which is the main mode of growth on the early black holes at this early cosmic epochs. So what we wanted to do is to search for synthetic counterparts in our catalogs of these extreme systems, and I'm showing you here the comparison in terms of black hole mass and stellar mass, and especially for systems that we expect in our catalog to be observable within these surveys of interest, both for an Eddington-limited accretion scenarios and for a super Eddington accretion scenario. And what we find is that basically what we want to do is also to track for the best candidates of these two extreme systems the evolution in time of the black hole and also its spectral properties. And so I'm showing you here the evolutionary tracks for our best synthetic candidates, which are respectively the blue and orange lines for the different accretion scenarios. And this is a pretty, let's say, crowded plot, but let me focus your attention on what we found is the maximum observable redshift at which these two surveys should be able to find accreting black holes, assuming the two different scenarios of black hole growth. And basically, if you assume a standard Eddington limit accretion, we found that these systems should be the most massive and most extreme ones in terms of redshift that these surveys should be observed to predicted to find. And so in case we start to observe more systems like that, or even slightly more extreme ones in terms both of mass and redshift, this might be a strong smoking gun for the fact that this system need at least some brief period of very efficient enhanced accretion at super Eddington rates. And in the first case, they should be, in an ideal limited scenario, the actual progenitors of the massive billion black holes or quasars that we observe at smaller redshift. And finally, in terms instead of spectral features, coupling cut predictions with the cloudy photoionization code, we've been able also to reconstruct the spectra of our best synthetic candidates, and we can compare that with the GWST photometry, both assuming different accretion scenarios, as you can see for the system on the left, but also comparing both the extended component coming from the galaxy emission and the point source component coming from the AGN when we have both available, like in the case of GNZ11. And what we are doing now is actually to make a systematic analysis on the properties of this population of faint quasars to find their typical spectral features and try to develop some dedicated diagnostics for the detection of similar systems also in fainter galaxies, since it has been shown that standard selection criteria are not that reliable at this high redshift to disentangle between just star-forming galaxies and AGN host. So I'll leave you with this, and for any curiosity, feel free to reach out and ask me. Thank you.
Thank you very much.
Is in this session, but anyways, well, basically here we propose a scenario where massive black hole formation occurs in situ in galactic nuclei, where nuclear star clusters are too dense to be globally stable against collisions. So, well, this is just a plot of mass versus radius. The red dots are nuclear star cluster and the blacks are massive black holes. So if we take the definition of collision timescale from Binet-Tremaine and we compare that to TH, which is the age of the system, we can derive the following expression. And if we plot this expression, we can see that these lines separe very well the black holes and the nuclear star cluster. So basically, this zone is where the collision timescale will be shorter than the age of the system. So this system here will be globally unstable against collision and will collapse forming a very massive object. We can do a similar process with the relaxation timescale and derive that green line there. And if we take the triple equality between timescales and TH, we can derive the following expression that match very well with the intersection of the other two lines, and also with the upper limit for nuclear star masses observationally derived by Nathan Late in 2012. So, well, this also can be interpreted as a critical mass. So when you cross this line, you know that your system will be too massive or too dense and will collapse. So these are two quantities that I want to introduce. Well, this already mentioned it, is the critical mass, and well, the black hole formation efficiency, that is just a way to measure the mass of the black hole against the star surrounding, okay? So Well, basically, this is our initial conditions. We test this with embodied simulations. And, well, after the simulation, we plot the initial mass against the black hole formation efficiency. At first glance, that look quite interesting, but what happens if we normalize by the critical mass? Well, we can see that this shows a very nice trend. But what happened with the observational part? Well, we do that using this simplified assumption, like the initial mass is the mass of the current black hole and the mass of the plus the mass of the current nuclear star cluster. The initial radio was 10% shorter than the current radius, and also we take at the age of 5 gigayears. So with this assumption, we derive this fraction of masses and also this black hole formation efficiency, and we can see that match very well the observation with our simulations. So, well, this is the summary. We propose a black hole formation scenario where massive black holes are formed in situ in galactic nuclei through catastrophic runaway collision in nuclear star cluster that are too dense to be stable. And we test the scenario with direct embodied simulations that we found the black hole formation efficiency grow drastically when pH is comparable to the collision timescale, or when the fraction of masses of the initial mass of the cluster and the critical mass is similar to 1. So if you want more information, you can check the reference of Andres Scala or my paper that was published like some months ago. So that's all. Thank you for your attention.
Thank you. So now we have Dimitrios Iordatou from University of Helsinki, and he will tell us about how we model relativistic accretion disk around spinning supermassive black holes in galaxy formation simulation.
Yes, thank you. Hello everyone, I'm Dimitrios. It's been a pleasure being here the past few days, so thanks the organizer for giving me the opportunity. And yes, is yet another subgrid model for how to model accretion disk in I thought it was on yeah, okay, a lot better. Yeah, about modeling relativistic accretion disks. So there have been quite a few talks about KETU and how it is able to capture this small-scale dynamics around single and supermassive black hole binaries. But I'm also here to promote rabbits, which disappeared. There it is again. RABBITS, which stands for Resolving Supermassive Black Hole Binaries in Galactic Hydrodynamical Simulations. And you probably never heard of it. The reason being that no papers have been submitted yet, but at least Shihong Liao, who is the main leader of this series of papers, will be submitting a couple of papers in the next couple of weeks. There have been quite a few talks in this conference about gravitational waves, recoil kicks, accretion, luminosities, post-Newtonian corrections, and spin is a fundamental parameter in all these general relativistic effects. And something we've been missing from KETU was a physical model to evolve our spins, like has been a bit ad hoc. So my project has been about developing and implementing a model that kind of improves on that. So in our simulations, we follow the formation and evolution of accretion disks. So our accretion disks now are part of the simulation, have their own properties. And here I have, for example, on the y-axis, the mass of the accretion disk as a function of time. We capture SPH particles, which is these red points, from the surrounding environment around the black holes. And as you can see, there are these vertical icicles type of things, which if you zoom in time, you just have the mass of the accretion disk decreasing. So we'll explain how we're modeling our accretion disks. In the standard alpha disk kind of philosophy, in order to build a global structure, like to have a structure for an accretion disk around the black hole, you combine locally valid solutions. So these solutions has to do with the assumption you made about the pressure, like radiation, gas pressure, and two mechanisms for the opacity, like from free and electron scattering. And the combination of these gives you three local solutions. In order to create a model, you need to know where these solutions are valid within your accretion disk. So just to give you a visualization of how this works, the model has 4 parameters that go in: the mass and the spin and the accretion rate of the black hole, and behind my face there, it should say viscosity. So that's the viscosity of the accretion disk. Just because it's hard to visualize a 5D space, I've kept the black hole mass fixed 10 to the 7 here, and feeding some accretion rate viscosity parameter. So I'm only plotting spin on the y-axis as a function of radius. The accretion disk starts a bit inside the horizon, which is this dashed red line, and stops at the self-gravitational radius. So for each radii within this space, we know exactly where these locally valid solutions exist. So by knowing these, the ranges of these limits, we can combine these together to then create, it doesn't look very clear, but to discretize the accretion disk and have the global structure by combining the locally valid ones. This is very useful because once you know the limits, you can then combine piecewisely surface density profiles. So you know the solutions from the Kerr metric and how mass should behave depending on the properties of this accretion disk. This is again the same example. We've also extended the solutions within the ISCO, this intra-ISCO regime, so we go all the way down to the photon radius, but you see the surface density decreases very rapidly, so it doesn't highly contribute, but it just makes our model more physically motivated. And being able to have the surface density profile of an accretion disk allows us to integrate the angular momentum profile. This takes me to the next step, which is how we actually end up feeding our black holes by modeling the whole structure of the accretion disk. So this is the plot I showed in the beginning. The mass of the accretion disk just going down and have these accretion episodes. And once you know and you have modeled and evolved the structure of the accretion disk, every time some of the simulations, we know exactly what the angular momentum of our accretion disk is. We can plug that in the formula developed by Fiacconi et al., along with the mass of the accretion disk, mass of the black hole, and the radiative efficiency. So we're able to capture SPH particles from the environment, then calculate the full relativistic structure of an accretion disk around a spinning black hole, take this information and use the structure of the accretion disk to feed our black holes. And an additional benefit, along with other you can get from that, is evolving the spin, like the dimensional spin parameter as a function of time. And the spin changes due to two mechanisms apart from the accretion and whatever angular momentum you have at the ISCO. You also have the Bardeen-Pedersen effect, this cross product of the angular momentum of the accretion disk and the spin times the surface density. And now we're able to fully integrate this profile. We know the warp radius that changes from aligned to misaligned accretion. We evolve fully this. So we're able, at each time step of the simulation, to know which part has aligned and which is still misaligned, and create this torque between the black hole and the accretion disk. So now our evolution of spin, this is just an example of one setup, Milky Way type galaxy, how that evolves more completely. I think I'm out of time, so I'm gonna leave you with a few summary points. Thank you.
At the moment, there are not really important announcement. I think the food is almost ready. They probably need a few more minutes, but you can slowly start to go out and get some fresh air if you like.
and the stuff and few other things, and I didn't manage to sleep well, and therefore I realized that maybe I'm not that young anymore, and since quite a while, as a matter of fact, and therefore someone will take my place after 9 YAGNs, and that someone is the only speaker that spoke at every single YAGN we had in the past and we are currently having now. This is the overview of what we did up to now, and the person is Matteo Bonetti. So, just a comment. The place we are going to advertise today could not be the next one. Maybe there will be a new one somewhere else covering another region of the world. You could guess, but there's a question mark, so, I mean, you can guess, but maybe we're wrong. And now, the stage.
Okay, so this will be for sure the place for a YAGN meeting. We don't know if it will be the next one, but for sure there will be a meeting in this place. So, any idea? You have to guess. You can see a medieval cloister. No. I don't know actually. Romantic church. I don't know. Maybe we can give you another hint. So, no, unfortunately not. No. Another hint. Maybe this is not a river, but maybe it's a lake. No. But close. Yeah. There are mountains around the lake. Din, 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 din. So, well, we don't know if it actually will be the YAGN 2024, but at some point, well, it's okay. Okay, we are sure. Maybe one before. Okay. So, for sure, we will see here in September 2024. Maybe before, we don't know. Okay, and done. End of announcement. Thanks.
So I can introduce you, yes. So we are now starting with the first speaker of the afternoon session. We have Eleonora Parlanti from Scuola Normale Superiore in Pisa, and her talk is about exploring AGN properties with the first JWST near spec GTO observations.
So, okay, thank you very much for letting me talk. today here in Young AGN, and today I will talk you a little bit about JWST observations. I was expecting maybe some people already talking about this, but no, only X-ray this morning, so that's So first of all, I will do a little bit of introduction between about the black hole and host galaxy coevolution, and then I will stop a little bit to focus why it is important to go at high redshift. And at the end, I will present also JWST's nice spectra of AGN. So first of all, as we all know, there are some scaling relation between the black hole mass and the host galaxy properties, and the tighter one is the one between the black hole mass that we have on the y-axis and the velocity dispersion of the stellar bulge of spheroids in the host galaxy. And this relation is very tight at low redshift, but looks like it's okay also for high redshift sources. Like for example, here we have galaxies at redshift greater than 4, which have a broadline component observed with JWST, and looks like the black hole mass sigma relation is still okay, even at high redshift. And also we know that the black hole mass is related also to the stellar mass of the host galaxy or the spheroids, the spiral, depending on which galaxy we want to observe. And roughly the black hole mass is 1/1000 the stellar mass of the galaxy. And as other people already shown, this is not the case anymore at high redshift. In yellow we have, and yellow and blue we have the JWST new data, and while in red we have the local classical relation. So it looks like this is not holding anymore at high redshift. But on the other hand, we know that galaxy and black hole must co-evolve for some times, because still we see some scaling relation. Moreover, we know that they are both fueled by the same thing. So availability of cold gas in the system fuel both star formation. This is the star formation rate density that you all know across cosmic time, and this is the black hole accretion rate density. And yeah, they both peak at redshift 2 and 3, so we know that there is something in common between them. And what I want to focus today is the theoretical scenario in which that explain how we can go from merger galaxy at a very high redshift, then they became dusty starburst galaxy, because when they merged, they trigger episode of strong star formation. And then I will go back to what dusty starburst galaxy are. And the strong feedback from the accreting black hole then can blow up all the gas and the dust that there is in the system, so the galaxy can shine as a beautiful and bright quasar at high redshift. Then this gas that is blown out cannot more trigger star formation, so the galaxy became quiescent and formed the local elliptical galaxy that we see in our universe today. And I would like to focus more on this phase with JWST observation that we have now. So first of all, let me explain a little bit. For dusty starbursty galaxy, I mean galaxy with star formation of 100-1000 solar masses per year, so very star forming. So since they are very dusty, the light that stars are creating in UV is then reprocessed and then re-emitted in far infrared. So we also call them sub-millimeter galaxy, because we identify them as bright sources in observing with them sub-millimeter bands. So they also called sub-millimeter galaxy. Let me stop a little bit. So why it is important to go to high redshift? The first thing is that not all the local relations that we take for granted at low redshift are holding up anymore. And yeah, but still we expect some connection. And we still need to prove this theoretical scenario that for the galaxy and then quasar coevolution. So let me present, So let me present you this source. This is ALES 073.1. This is a very good studied source. It's a SMG galaxy at redshift 4.76 with high star formation rate, 1000 solar masses per year, and high luminosity, and also 10 to the 11 stellar mass galaxy at redshift 5. So we have all possible ALMA bands observation. And we also have a C++, which we can also trace the kinematics with, and it's a very nice rotating disk at redshift 5. Moreover, is also hosting an AGN inside. There is some detection of X-ray emission of ionized iron lines. And so we have this X-ray luminosity 10 to the 44 ergs, that then with SED fitting we expect a volumetric luminosity of AGN 10 to the 12 solar luminosity. And importantly, this NH is quite high, so what we were expecting was a quantum thick AGN in a sub-millimeter galaxy at redshift 4.76. And now here we come the JWST observation. We have IFS, so that means a cube, so spatially and spectral information of the source. And here you see the H alpha complex, and as you can see here, we see a beautiful broad line around H alpha with a full width of maximum of 1,000 kilometers per second. Some sign of outflows also here plotted in fitted in green, with full width of maximum of 500 kilometers per second. And unfortunately, we don't have observation. We have observation of O3 in H beta, but it's not detected. So it was very hard then to give a right value because we don't know how much to correct for dust obscuration. So this is the H alpha flux, and thanks to a spaxel by spaxel fitting, we can take into account the host component. So you see here the flux of the host galaxy in H alpha in nitrogen, the flux of the outflow, and the flux of the borderline region. So we can detangle between all of these components. And let's look at the BPT diagram. So no one talks. I've talked about this in this meeting, I think. So on the y-axis, we have the ratio between the flux of the oxygen tree and the H beta line. And on the x-axis, we have the ratio between the nitrogen, the flux of the nitrogen line, and the H alpha. And what is telling us? Well, here you see underlying here in the gray contours, the SDSS points. And these separation lines, the dot, the dashed lines, are different for different authors, but what they're doing is they are separating between AGN, which lies on this side of the plot, and star-forming galaxy, which lies on the other side of the plot. This is due simply to the fact that AGNs emit harder radiation than normal star-forming galaxies, so the line ratio of this line will change. And unfortunately, this does not work anymore at high redshift, because here you see the Cameron points, which are representing normal star-forming galaxy at high redshift. But we are lucky, because we have a very metal-rich galaxy. So for metal-poor galaxy, this don't hold anymore. But we are lucky, we have one solar metallicity, more or less, even at redshift 5. So we can use it. And ALES lies here. As I mentioned before, we don't have like a point, but we have a limit only because we don't have H beta. And this is the central region, while this purple band is the outflow. Of course, we have very poor constrained values for the outflow, but what is striking us is, yeah, it's laying in the AGN side of the plot. And so I can do this together. So if you look here, this histogram under here represents the number of points in which we have, like this yellow value is a composite value. If the value of O3 is like the central region, we expect it to be AGN also. So we see that the host galaxy is still dominated by this AGN radiation. And more importantly, the outflow is very, very red, and red means very high values of nitrogen over H alpha. That means that is highlighted by the AGN. So let's go back a little bit to the M-star black hole relation. So what we have here is the region where the local broadline AGN lies. Here instead is where the local spheroids and spiral and high redshift bright quasars lie. here, as I mentioned before, the Maiolino and Aricane and other people's, oh God, other new observation from the WSTLIs, and ALES is in this region. So we are expecting ALES to be like comparable to a powerful quasar, but it's not. It's not actually a quasar. We see a broadline region, but it's not that bright. And moreover, we have sign of outflows, as I mentioned before. Unfortunately, this is marginally resolved, I'd say. Is quite fast because it has 1,700 kilometers per second, but it's quite weak compared to the star formation rate. So the mass loading factor, which is the ratio between the mass of that is brought away by the ionized outflow and the star formation rate is only 1%. So from a first calculation, I was thinking, well, it's not doing anything. So this outflow is very weak. It's not enough to justify then the evolution to the bright quasar. It's not acting right now. But actually, it seems it's starting to do something. So this is the velocity dispersion profile. So I would like to stress you that this is intrinsic. So it's corrected for beam smearing, for the spectral resolution and everything. So this is the fit results. In red for the H alpha line, in blue are all the fit with the C plus line. So the red one is tracing the ionized gas that is in the system, while the C plus line is tracing the colder gas, so neutral or molecular gas in the system. And what you see here is very strange. In the central region, we cut off this part which is dominated by the PSL, so we don't know if you can really trust it. But here, up to 1.5 kiloparsec, what we see is that the velocity dispersion of the ionized gas is 2-3 times higher than the one from the neutral phase. And well, we thought that maybe we did a different analysis in respect to to LLE21, so maybe this could be the discrepancy. But we also look at the observation. So this studies the observed H alpha velocity dispersion map. This is the observed C plus map, and they are both rebinned to have the same pixel size and the same beam smearing, so the same level of beam smearing. And here you see the difference. And you see that, yeah, there is a region in the center where the difference between them is still high, is 100 kilometers per second higher than the other one. So maybe are we witnessing the onset of the AGN feedback? So this outflow, as we think, is not powerful enough to halt star formation or halt the inflow of cold gas. But what is trying to do is just increasing the velocity dispersion of the ionized phase of the interstellar medium, which is the less dense one, because it's not able right now to affect the most dense part of the galaxy and then halt star formation. So I can give you my summary. We find a broadline optical AGN, but that is obscure in X-ray, which that was a little bit surprising to me at first, but then I saw that it's not that rare, but it's not that common also, so don't know. The black hole is still overmassive compared to the stellar mass of the host galaxy, as for other high redshift AGN, bright quasars, or other AGNs found by the WST, and also we find signs of feedback from the AGN, supporting the scenario in which AGN feedback then eventually will halt star formation and expel the dust and gas in the system and make this galaxy shine as a quasar. So thank you very much. I'm ready for questions.
Thank you, Leonora, for the
Our next and actually last speaker for this session is Junian Hyung from University of Texas in Austin. And his talk will be about observability of low luminosity AGN in the early universe with JWST.
Yeah, thank you. Thank you for giving me this opportunity to talk. I'm Junyoung Jun, and I'll be talking about my paper on this observability of low luminosity AGNs in the early universe JWST. So I'll start with the motivation of why we want to observe these high redshift AGNs, like similar to the previous talk. So we see that AGN feedback is very high in the local universe and probably is also in the high redshift universe. We expect these feedback from these AGNs to have a huge impact in the evolution of the early universe, on star formation, on its possible contribution to reionization. And then as we see the scaling relations to the local universe, there may have been this co-evolution between the AGNs and their galactic counterparts. So the best way to study them will be, of course, to be able to observe them all. But then there's problems with that because at high redshift, things are much more difficult to observe. And then as you go to higher redshift, if you see on the left plot here, you see that the dust mass generally can go much higher. And then a lot of AGN fraction can actually be obscured and be difficult to observe, even if they are bright enough to be observed at high redshifts. So an alternative way of studying these high redshift systems will be through theoretical methods. So you can use analytical models here, which for my previous work. But also you could use cosmical simulations, which will be the focus of my talk this time. So what the specific question I try to address is the growth of high redshift supermassive black holes in the early universe. So I think this plot was shown before as well. This shows observation from the JWST of a high redshift AGN that's pretty massive. And to be able to reach this high masses, you either have to have a stellar mass, like a standard stellar remnant black hole, growing at some phases of super Eddington to reach this high mass, or have some exotic seeding mechanisms, such as a direct cluster black hole starting at 10 to the 5 solar masses, growing at Eddington to reach these high mass solar mass black holes. But for this talk, I'll be focusing on these low mass black holes growing not as super Eddington, but more seeing what the, I guess, more average growth might look like. Because currently, these high redshift observations are probably biased toward the more extreme and bright objects. And we expect that there most likely exist more objects that are low luminosity and have much lower accretion rates. And I hope to see what their evolution might be at high redshift and also test to be able to observe them with the new JWST. So this talk is based on this paper here. You can see my co-authors who helped me in this work. And then we will use a cosmical simulation to simulate the growth of a black hole in a typical cosmical box representing a cosmical environment. So specifically, we use the Gizmo code, which is a Lagrangian code, and we use the meshless finite mass, or MFM, hydrosolver. And when you use the modified version of Gizmo used in this paper, Leo and Brahm, you can check the full details of the modifications here. But quickly, there's new models for star formation, cooling, metal enrichment, and all that. And what's relevant for us here is that they include POP3, or the metal-free star formation, so the very first stars that will form. And then because we can't resolve individual stars in this simulation resolution, the star particles in this simulation represent stellar clusters or stellar populations. And then, of course, we include feedback, photoisolation feedback from these stellar clusters. So there's an H2 region around them. There are also supernovae feedback, so that you can have a larger radii of stellar feedback in the cosmical box simulations. And also for POP3 stars, we utilize a more top-heavy INAF. So that from POP3 stars, we can get slightly more heavier seeds, which we believe to have existed in the early universe, and some of them may grow to be those massive high redshift SMBHs we see. And you can see some specific parameters of the simulation code here. So it's around the 11 megaparsec cube box. So it's not at the scale of very large cosmical simulations, but it's small enough so that we can resolve pretty high resolution for a cosmical box simulation. So what we specifically do is we start with an initial condition box with some density fluctuations. Then we evolve this box until when the first star started to form, around redshift 15 or so. Then we identify the dark matter halos in that simulation, and we choose the most massive one at that point. And then we turn the most dense gas particle in that dark matter halo to be the seed black hole. Then we test 3 different seed black hole masses from 10 to the 2, 10 to the 3 is like, I believe, like the upper mass of POP3 stellar seed black holes, and 10 to the 4 maybe it's like a very high stellar cluster, possibly black hole for seed. So, and then we see whether these black holes will be able to grow efficiently in this environment. So we insert a black hole there, and then we evolved it more to see how, if you see, maybe a little bit hard to see, but there's inside the dark matter halo here, how the black hole may evolve in this cosmic web. For growth of black holes, we use a usual Bondi hole accretion Eddington rate limited by Eddington accretion, and that's you can see the formula here. We actually don't consider this gas velocity here, so the growth is only mediated by the sound speed at that point. But we chose that because, as we'll see soon, the black holes don't tend to grow, so we try to see what the most optimal growth of them may be. But in that case, still they don't grow. And we also include thermal feedback from the black holes so that based on their accretion rates, they can impart energy to the nearby gas particles. But again, with low accretion, that doesn't seem to matter that much. So you see the mass accretion rate on top here in the black hole mass growth. So the blue lines are the actual results from the simulations, and the red lines are the Eddington growth, if they were to grow at Eddington. And then you see the mass accretion rates are generally some magnitudes below the Eddington accretion rate. And compared to exponential Eddington growth, the growth of the seed black holes are generally flat and probably linear. You can see the growth more clearly here. So we show the mass ratio between the black hole mass and initial mass. And we see that the black holes don't even grow to twice their masses throughout this, I guess, long cosmic period between the redshift 15 to around 6 and 5. And then we see the Eddington rate, we plot the Eddington ratios of the black holes here. And generally, they grow, on average, they are at a 1% Eddington ratio. So again, because of that, these black hole growth are very limited and then don't grow to be these high redshift supermassive black holes that we observe. So we compare our simulation to various observations. There's a lot on this plot, but this blue line is the mass evolution of the halo that we put our black holes in. This yellow line is a stellar mass of the halo. And we compare that to the JWST observations from the Sierra survey. So these are the dark matter halo masses inferred from the Sierra survey, and these are the stellar masses from the Sierra survey. And we see that our halos are generally much lower in mass compared to the observations, which was our goal, because JWST observations will be biased towards the higher masses, and then we wanted to see what the more common lower mass objects would be like. Another thing to notice is that we have a significant stellar mass. So the stellar mass is around 1% of the total halo variable mass. So we expect there to be a lot of stellar feedback going inside that halo. We also plot various JWST observations here in blue. This black is a Larsen et al. AGN mass, and then this yellow star is a stellar mass inferred from that. Then we also plot the GNZ11 AGN mass and the stellar mass here. And again, compared to these dashed lines show our black hole mass growth. And compared to this, these lines are, compared to observations, our black holes are much lower mass, much lower accreting black holes as well. And compared to the high redshift quasar observations as well, seen in the red box region here. We also compare our black hole masses against the local M sigma relation. They do deviate from this M sigma relation, but we are not quite sure how significant that may be, because M sigma relation is from a population of black holes. But then in these cases, we only submit one black hole, so we test one black hole at a time. And then we do see them crossing the M sigma relation at least at one point during their lifetime through their evolution. Now from these growth, why do they not grow? We believe that's because from the stellar feedback. So we plot the temperature density plot of the cosmic region or the dark matter halo here, specifically the dark matter halo itself. So the gas temperatures inside the halo are generally high from stellar and supernovae feedback. And then we plot the stellar mass density here. And then of course, with high stellar mass or near where the black hole is, the gas will be heated. And if you look at remember the Bondi-Hoyle formula, the heated gas will generally have lower densities and higher sound speed, so they will decrease accretion. So at these, I guess, low mass halos, the gas really can't accrete well into the black hole, and then the accretion and the mass growth is low. We also show the temperature density gas temperature density phase plots here. So here's the hydrogen gas density in the x, and the hydrogen gas temperature in the y-axis. And this is at redshift 15 when you first insert the black hole. And this is the end of the simulation around redshift 5.6. In both cases, we see this high temperature 10 to the 4 gas, hydrogen gas, which corresponds to the gas heated from stellar feedback effects. And then these high temperature gas won't be able to easily accrete onto those black holes. And that exists from the start as well. So throughout its whole lifetime, these high temperature gases exist and won't be able to accrete efficiently into the black holes. We could try to insert the black hole at earlier times before star formation so that all the gas is in this cold phase. But again, for stellar seed black holes, we want stars to form before we insert the black hole as well. So here we'll show some, animations of the evolution of the halo. So you see the gas flowing in the halo as it grows through the cosmic time, and the gas is heated. And then while there's large amounts of gas inflow, the black hole doesn't really get to accrete much of that. And here's the evolution of the phase plot. And you see the cold gas inflow into the halo, but then gets heated by the stellar feedback. And then, of course, this feedback-heated gas, again, can't accrete efficiently into the black holes. And then also, because it's a cosmic simulation, we can change the physics. So we decided to test what the effects of how significant the stellar feedback effect is, and decided to try to turn off the stellar feedback in this black circle region around the black hole, and see what the growth may be in that case. But in that case as well, the black hole doesn't grow because the black hole seems to wander away from this gas density center. This low mass black hole, I think this is the case for the 300 mass solar mass seed. And then this black hole doesn't stay inside this high density region, but wanders around, and then of course can't grow even if we neglect stellar feedback in this case. And now that we have these mass growths, we can now test the observability of JWST from JWST. So we use this multicolor disk model to calculate the fluxes that we may observe. And this flux value this equation depends on the mass of the black hole and the accretion rate. So this is a phase plot of this equation right here. So we have the mass of the black hole here and the mass accretion rate here. And we plot some lines to clarify. So this is when the 1% Eddington corresponds to what we see here. This is the Eddington rate here. For sanity check, we also plot the large Nadal AGN here. They believe that to be accreted close to Eddington. And then because this is to the right of this JWST filter sensitivity here, this large Nadal AGN is expected to be observed in our model, which is consistent because it has been observed. But our AGNs that we simulate in this 1% Eddington region is very unlikely to be observed. As we see here, this limit here is 10 to the 4, and it's much lower than what can be observed over left to the right here. And we especially plot the evolution of this flux across cosmic time. And this is for the F200 filter, JWST F200 filter limit at 2 microns. So our fluxes are these jagged lines here, and they're, again, much lower than than the JWST filter limit. For reference, we plot the Eddington fluxes. The fluxes these black holes will show in case they're accreted at Eddington. And in that case, they will be observable. But again, there will be the extreme cases as well. And our black hole masses, we plot for reference here compared to these accretion rates. According to the fluxes, again, are pretty flat. We also have these direct class black hole analytical model here for comparison. Again, similar to these Eddington growths, is also expected to be observable. So how can we get this Eddington growth? Of course, there may be cases of this exist. Maybe there are magnetic hydrophobic simulations at much higher resolution, which show with magnetic fields or dense non-uniform density of the black hole, they can accrete at super Eddington or Eddington rates to be observable. But again, these are much closer in and don't resolve the cosmic environment around the black hole. So it's unclear if these environmental conditions can really exist. Because even if you can have these high accretion rates, there has to be enough gas inflow into the dark matter halo so that this growth can be sustained. Again, these will be the extreme cases that we are currently observing right now. So for what about these low mass black holes, they may be observable with through gravitational lensing. So this is the Arundel star, which has been supposedly single star at redshift of 6 that have been observed with the JWST through extreme gravitational lensing. So because AGNs are point star, and stars are both act as point sources, maybe with the right conditions, our low redshift, low luminosity AGNs will also be able to lens this much as well, extremely lensed. So we just plot the lens fluxes here compared to our fiducial fluxes there. And then with extreme lensing, some of them may be observable at high redshift. But again, this is a very unique situation. We don't really know if this situation will exist anywhere in the universe. So to conclude, we see that typical low mass black holes in the early universe generally do not grow high enough and fast enough to be observed with the JWST. But then there are other considerations we will have to make, because so generally AGNs sit inside galaxies, and there will be galactic stellar fluxes that may overshadow the AGN flux if it's absolutely observed. We haven't considered that because even with the AGN by itself, we see that they won't be observable. But for these, if we want to test more highly accreting extreme AGNs, we'll have to consider the stellar luminosity from the galaxy host, the dust obturation as mentioned earlier, and possibly what the population, what the number density of these AGNs will be to test the observability of the more massive high redshift AGNs. And again, the next steps of this work will be to see what environmental conditions allow for these super Eddington or Eddington accretion so that they are observable in contrast to these low mass black holes. Thank you.
discuss with you. They can be a bit biased, perhaps. So if you have also other points that you want to discuss related to that, or even not, I mean, you're welcome to do it. And I would like to start, since I saw a lot of interesting talks related to high redshift sources, and also in different wavelengths, showing that there are a lot of similarities with sources at low redshift, but I saw also that there are some differences. So I don't know, these differences that we saw are real or not. There are some effects like selection effects, the quality of the observations, or the model also that we use to analyze these observations. So what do you think about these points? I mean, any ideas? Someone want to start?
Well, also to the people that actually model or do modeling of black hole growth or whatever. Are you surprised? Are you happy? Is it controversial for you that AGN high redshifts are so similar to AGN and lower redshift? Is this something that surprises you? Or even though there are differences, as I said, but these differences can be peculiar cases or not. So what do you think about it?
I don't work on black hole growth modeling, but to me, it's not surprising that IGN at high redshift are different from, yeah, exactly. The gas is a spiral, so maybe exactly. I don't believe there is a dependence on physics on the redshift. Maybe someone else thinks something else.
Physics depending on redshift. No, I actually do agree on this, but is it something that we expected or not? There are some differences those in the spectra. So are those differences due to extra physics that we are not understanding well, or and what this physics will be? Outflows, now everything that is ignored or not explained, oh, there is an outflow in it, that's it.
Or maybe we are looking at weirdos.
Oh, yeah, I don't know, peculiar sources.
I mean, I guess it depends also on not on the physics of the AGN at high or lower redshift, but also on the diagnostic we use, because actually if you look at the BPT diagram as it was shown, it'd be very difficult to disentangle between just star-forming galaxies, but very metal-free at this higher redshift when you have very faint AGN. Basically, we're talking about very faint accreting black holes, while if we're talking about quasars, okay, they might be more self-similar, but those very faint ones, I mean, on the observer point of view, there might be some different diagnosing that we have to use to detect actually them. And this difference, I mean, it's not the physics on the accretion, but on the host galaxy, which might be for bulk of the system much more metal-free. I guess, I don't know you.
Well, diagnostics are based on low redshift AGN because of the lines that can be observed. And it is now that we are start to having statistically significant samples of high redshift sources, but we don't have the full broadband spectroscopy to cover the crucial lines. So this question is,
yeah, it would be nice for us to know what kind of lines we can test to see if we have different diagnostic, like highly ionized lines. There might be, something we see if on our synthetic models there might be some differences. within the classic star formation star forming population on AGN host, or?
You can try with synthetic models, right? So you take your synthetic models, you smear them with the PSF of the instrument that you prefer, and then you start to look at what diagnostics we should look at, because it's for us is, I mean, it depends, no? Depends on the instrument, depends on the coverage, as I said, but this goes back to the last point, actually, which it goes back and forth. Actually, this last point is not the last. It goes with all of them. So with all the 3 points that you see listed here, what would be the synergy with theory? Because otherwise, and especially a high redshift, do you believe in black hole masses? Do you believe in the values of the black hole masses that observers are measuring? But why? We are measuring 10 to the 10.
And also on the stellar masses, I know how much that depends on the star formation history you assume for your set-fitting model.
So you will place your hand on fire. Yes, this is a 10 to the 10 solar mass black hole.
Well, there is one, which is APM, the telephone number I was talking about. They measure the black hole mass from reverberation mapping on S4, C4, something like that. So, I mean, that's 10 to the 10. And then it's also consistent with single epoch black hole mass. So I would trust that more than other diagnostics on other AGN and high redshift. Then the question is that an outlier? Is that overmassive, or is it not? But I have no idea about the rest, to be honest.
Since the mic is here. No, I just wanted to say that even in the local universe, when we talk about virial masses, single epoch, reverberation even, there is always this 0.5 dex. So can you put your hand on fire? No, I wouldn't. I would put my hand on fire just with the dynamical ones. Otherwise, no.
Well, but 0.5, that is the accuracy on the absolute value, right? No, that's okay, I understand that. But if it's 10 to the 10 plus or minus, like this value is not that, it's not helping much anyway. But I would like to go back and forth. So we have observers here, we have models and people that work on simulation. What is the parameter that you really want as a constraint for your modeling to be more, I don't know, accurate? Or what should we do? I mean, we should work a little bit more, together, or these are not two paths that goes in parallel, to be honest. So, like spectra, yes.
Well, given that to describe a black hole you need mass and spin, right? Of course charge, but I don't think anyone is working with charged black holes. So I trust masses, but then spin is, I think, the parameter that hasn't been constrained as well as black hole masses have, especially if we discuss about high and low redshift. So I think that will probably also go back to all the way the seeding of the black holes, how the seeds are formed. If it's just a POP3 star, I assume they'll have different spin. If it was like a remnant of a star, they'll have different spin value than it came from mergers, if the mergers have spun up or down the black hole. So I guess spin is equally important as masses. If you can do something about that, will be appreciated.
Something else?
It is indeed a very interesting point, and I would love to have measurements of the spins. One point, though, that we have to keep in mind is that if you accrete twice the initial mass of the black hole through coherent accretion, or 10 times the initial mass of the black hole through isotropic accretion, you erase the information about the initial spin. So my guess would be that any observation at redshift 6 of a black hole of 10 to the 8 solar masses or more would have absolutely no information about the seeding mechanism, true spin, whatever. That's my impression, because it had increased its mass by at least by a factor of 10. And if I may continue, I have a curiosity that is unrelated to the current question, but what is the object for which we have reverberation mapping at high redshift time masses? The object that you were quoting, for which we have the reverberation time delay. And the reference is Saturni. So the first one is the single epoch, and the second one is the one. Okay, is the campaign. Okay, thanks.
So regarding spin, what we can do? What would be the wavelength if we can measure spin?
If you believe reflection measurements, although for quasars you don't really have strong lines, so I don't know. In X-rays, for X-ray binaries, depending on the shape of the thermal emission, there is a way to measure the spin from the continuum. I suspect that this is too complicated for AGN, but yeah. But if there's any way this can be done, it would be amazing. I honestly don't believe it's possible. And when they are too bright, the iron K lines are too ionized. So I personally don't know.
Yeah, the iron K alpha. She was saying about the iron K alpha line, but you cannot do it at high redshift. That's the point. So maybe you can try to measure it at low redshift, but then you calibrated them. That's the point. I mean,
maybe it's not really high redshift, but like with lensed quasars, you can use microlensing of the iron K alpha line to measure the size of the disk, and I think they also have a measurement of the black hole spin, but maybe it's RxJ, so it's below redshift 1. So it's, but in that sense can be high. I mean, there's no other way of measuring that. And also thinking about the X-rays, another big difference between local low redshift and high redshift universe is the properties of the UFO lines. Because the UFO lines, the ones for iron 26, 25, like the main UFO feature, we have the equivalent widths that are above 200 electron volts, while in the local universe it's usually 40 or 50. And why? Is this still on? Yes. I mean, I don't have an explanation for that. Selection effects.
So there's one thing we need to take into the loop. Was hoping that it would come automatically. So I will just throw it in the loop, and it's metallicity. That is going to go against any kind of measurement with metals. So at very, very, very high redshift, the metallicity will go down. So it's going to be difficult to do measurements of stuff with iron, for example. Oh, I don't know.
I mean, in my mind can also be above 1, but then for someone else it's above 6. But then if you observe something in the X-rays at redshift 2, there's no, like with the spectra that we have, there's no way you can constrain the abundance of iron, for example, with the reflection models. So you just have to freeze it, maybe you can try and find a value, but then you have to set it because there's a way you can constrain it. So it's an issue that I don't think we can overcome soon.
Or maybe you can do something like stacking analysis, but then you don't have statistics.
Perhaps I was misunderstood. I was not talking of measuring metallicity. I was saying the other way around. The metallicity goes down before the peak of the star formation. And here we are talking of redshift maybe 6 or 7. So there, the iron abundance is going to go significantly down, even in the nuclear regions, I guess, where perhaps there was a burst of star formation. So measuring iron K lines to perform spin or whatever measurement at redshift 6 or 7 is going to be very challenging, I guess.
But do you think we're ever gonna see them? I mean, redshift 7. That I mean, I wished, but so far.
So the point can be, if we will be able to see a line, will we be able to see the line? There will be iron making the line. No, I was saying, if we will be able to measure the line at this redshift, the iron K alpha line, because we will implement our instrument to a level that will allow us. There will be a line or not.
To those who work on gravitational waves, if there's anyone here, I remember in some papers since the detections, there were some constraints on the spin. So I was wondering if this can be extrapolated to supermassive black hole when LISA will detect any merging. I was just wondering. I really have no idea. So perhaps some of you may know.
So the values of the spins that have been, the constraints that have been put on the values of the spins cannot be extrapolated, and we believe that the origin of the evolution of the spin would be different for massive black holes and stellar mass black holes. But the constraints that are put from ground-based detectors that are currently ongoing are very, very poor. While when LISA will fly, the measurements of the spins will be incredibly nice, meaning you will say the spin is 0.98 whatever or 0.735 and you will have information about the spins of the progenitors as well. But the one question, so of course, first of all, we have to wait until LISA will detect something. We cannot extrapolate the current data. One question that I ask myself is, will the population probed by LISA will have the same biases that we have for the electromagnetic one? Because that's not completely clear to me. Because in principle, we want to learn to infer something about the population of massive black holes, not of merging massive black holes, nor of close to adding to massive black holes and so on and so forth.
Well, but this is a completely open space. So even if you observe something that has selection effects, it's good if we observe something, because this is a completely like an open question mark. So
better than nothing.
It's a new discovery space. So can we go to the second point? Are you happy with Eddington or Bondi accretion or super Eddington accretion? Is there anything that modelers can do to do better?
I mean, these effective Bondi accretion models, I think they have a problem at high redshift, because if the seeds have a low mass, then the accretion rate scales with the square of the mass. It assumes spherical symmetry and things like this. So this is definitely something that we should move away from in the simulation community. And I think in the more resolved simulations, this happens and the results look qualitatively somewhat different. So Well, I mean, one example is there are papers where the effective Bondi model is used, and there's a boost factor introduced, which accounts for all the unresolved effects, including like unresolved interstellar medium, the cold phase, and things like this. And this factor can be in the order of 100 or something like that to facilitate the growth of black holes. There's no really real explanations for that. Exactly, you kind of need it. I mean, we have seen it in the talk. It's very difficult to grow with effective Bondi. I mean, potentially you can comment on that more, but we need. Yeah. I mean, zinc particles, for example, are an alternative to this, and I think that's what a lot of people explore now. I mean, if you want to elaborate.
Yeah, I think in many cases we should get rid of Bondi. Yeah, there's all sorts of models that are being tested now, cold accretion models, which will typically give you a higher accretion rate than just a standard Bondi if you don't have the boost factor. The models that we've been developing with the subgrid accretion disks, we calculate mass inflow rates on the scales of the accretion disk. Yeah, I mean, there's a whole host of different things. There are simulations that do combinations of hot and cold accretion. I'm trying to think of other examples now. But yeah, I mean, Bondi breaks down in so many places. And I think even in the local universe, you know, there are observations in galaxy clusters, people try and estimate the Bondi rate, compare it to the amount of feedback you're getting, and find the Bondi doesn't give you enough accretion, and you need something else to give you your accretion rate. So I think even in the local universe, Bondi isn't necessarily giving you enough in the galaxy clusters, for example, where you would think hot accretion is what's important. I think people are developing these models that are more physically motivated when you don't have spherical symmetry and when you have disks and different inflows and things. I think there's more to do.
I mean, we made this point a few times now, but I think the other aspect here for simulations is definitely dynamics, because if you don't have the black holes in the center, then your accretion model can be really good, but you will just not have any gas to accrete. So it's always these two things to consider at the same time, like having a good accretion model, having the black holes where we expect them, and I think this is where observations could help us if we knew something about the environments where we would find them, and know something about occupation fractions and things like this, such that we can get an idea how the populations... Yeah, at least, I mean, for the type of simulations that we are thinking about, I think that would be useful. Yeah.
Yeah, just one other point on growing these black holes and getting the accretion right. You also have to get the feedback right. You have very high resolution simulations where you have multi-phase ISM, and the interaction of the feedback, you have a jet or a wind, and how it interacts with high density material is very different to what you see in lots of low resolution cosmological simulations, which to some extent are like a 1D expansion of a bubble compared to a wind actually acting on the dense stuff that only feels the ram pressure, and a hot bubble that will clear everything out. So we also, I think, have to get the cold gas right, which is hard in low resolution cosmological simulations, but also the feedback, right, which can be very directional as well. And you know, only impacts a certain direction, then you can still have inflows, you know, in other ways. There's also, you know, in simulations where you see the promotion of the formation of cold gas from the feedback as well. And if this material can fall back in, it can continue to fuel the black hole. Well, yeah, also positively.
Yeah, because from observers, but correct me if I'm wrong, but we often see negative feedback. Positive feedback is something that we rarely observe in sources, and this is something that has been modeled. So is it a selection bias? Are we just selecting the ones where negative feedback occurs, and we are, for some reasons, not picking the one where positive feedback is occurring?
Depends also at the low redshift.
Well, there is one source that I know, NGC, no, it's the one observed by Cresci, published by Marcella Brusa, Cresci Maiolino, where positive feedback was detected, but this is the only one I'm aware of. Yeah, it's the only one.
Lower redshift.
Formation of stars inside the afro.
The one that you were mentioning, XID2028, there was a second paper by Schultz, Harrison, and the other people saying that Cresci got it wrong and there's no positive feedback. Because it depends on, I still have to figure out how, like all the analysis and things, but depends on how you treat the H-alpha, how you do the PSF, and how you subtract the AGN and all. So it's, I mean, depending on who you talk to, it's yes or no or maybe. So we don't really, I mean.
Well, this high redshift business is going to be the future for a few years for sure, so it's better we we have an handle on it. I've actually another question, which is out from the list, but I'm going to say it later. So, is there anything you would like to add on the role of any evolution of any parameter you might think, how we can model outflows or jets, or we say something already on super-Eddington accretion or Pauli accretion or whatever.
So maybe I have a question. If I mean, there are a lot of different models to explain the growth of this of the black hole mass of these quasars, and is there a way to distinguish from the observational point of view, maybe driven by models, how this accretion happen? If there is a way to distinguish the accretion, the phenomenon that was driving the accretion of quasars. To give an example, we know that from super-Eddington accretion we expect a lot of outflows and jets. So if we observe stuff with the signature of these outflows and jets, maybe we can think that the accretion of the supermassive black hole up to masses that we know 10 to the 9 could have been because of super-Eddington accretion, but maybe there are other models that imply other tracers that we can try to see. I don't know. This is a real question. It's not.
Well, I guess let me rephrase this. Currently we are able to distinguish between a few, probably, type of accretion just because of emission lines features. Nothing that is related to the continuum at the moment, I mean, from what I know. So one possibility is if you will model the continuum, for instance, is that you don't have any models for emission lines, which is probably too complicated because you have to implement a photoionization modeling, et cetera. But if any of you are able to provide integrated spectral energy distributions in the wavelength region that has been observed by, I mean, there are a lot of degeneracies, of course, but in the wavelength region where current telescopes are observing, and say for these kind of accretion, these are the spectral energy distribution that are modeled for these kind of black hole masses and accretion rates, for instance, or probably you have also spin in it, for sure. And that will help, even for the continuum, I guess. Then the additional complexities emission lines, which is currently the only smoking gun we have, because of the cell similarity of the continuum. So is this something that, for instance, we can break down with the models? Are the models saying anything different depending on the accretion? Because from what we saw, the continuum is outstandingly the same, regardless. So okay. And this is actually the third question.
Yeah.
If high Z quasar, I don't know how we are up with time, but how high redshift quasar could be highly accreting narrow line Cipher-1s, but scaled up in mass and luminosity. So I'm not sure. This is an extremely driven question, so I'm not sure if we are all on the same page on what is a narrow line Cipher-1 or whatever, but
let's just think about a source accreting at the Eddington limit or above or close to, but with a low mass, 10 to the 6, with peculiarities. So looks, I mean, with feature very similar to the one that we observe at high redshift.
I want to add some comments about this question because I don't know if we could derive the black hole mass directly through the broadband SED of agents, but I think when we consider any methods about this, we need to also include some degeneracies because from the observational aspects, for example, like we also need to consider the inclination angle effects because even if for the same type of agent, we look through the different inclination angles, we will find a totally different spectrum. And I think related to this super adenine like sources, probably there's analogic objects which is in the stellar mass, which is Eurolax, and Cho did a lot of work about this to find a lot. If we look at from different inclination angle, we will have a very different spectrum in the X-ray band. So I would say it would be very hard to derive supermassive properties just directly through the continuum. Yeah.
I agree. Indeed, when I was talking about, when I refer to the continuum models, I was thinking more of, I know black hole masses from emission lines. I know accretion rates from other indicators. And if I consider different accretion models from theory and I plugged in different black hole masses and different accretion rates, what the continuum will be, and then compare it with the observation, not the other way around. Does it make sense?
So maybe just about narrow line Seifert itself and measuring black hole masses in them. To do it in using optical data, you can do like reverberation mapping using H beta. And when you do it and compare it with radius luminosity relation, they don't match. So when you do reverberation mapping, you underestimate black hole mass of narrow. Maybe like you have two measurements for the same sources and they don't agree with each other, just for narrow line Seifert. So I guess when you go to higher redshift, maybe it's problem also. I don't know. I
Underestimate. That would be even worse.
Yes. Yes, that's true. Yeah. But when you check the radius luminosity relation for like the population of sources, the narrow line Seiferts are not matching the fit. Well, like all other sources are aligned. Like when you do reverberation mapping and radius luminosity relation, it's all good. But for narrow line Seiferts, it's something we don't understand. Maybe about geometry. Maybe we are measuring the radius of something a bit different. Yeah, I don't know. I don't have answer for this, but it's just something to work on probably. Because if we don't understand narrow line Seiferts, what to do about higher redshift when we don't have H beta? We have carbon, which is I don't know what problems could we have with this one.
Sometimes we also have magnesium. Magnesium depends.
So I agree. If I can add other uncertainties on top of those, the uncertainties about the inclination that you were referring to, that indeed had been proposed for narrow line Seifert ones as well, do apply exactly the same way, in the same way for single epoch and reverberation mapping mass estimates. So whenever someone comments about the fact that that mass is correct because it's been observed through reverberation mapping, the uncertainties about the geometry of the Brodmann region is in there as well, and applies the same way. On the other side, about the high mass, the high redshift systems, I have some ignorance here. So can you quote what are the similarities other than the fact that the accretion seems to be high with narrow line Seifert ones? Like there are enormously strong iron complex, or what are the similarities you're referring to?
Like for instance, the continuum, and the fact that if we superimpose I don't know, any composite or spectral composite at low redshift, you can pick your favorite, Vandenberg or Telfer, whatever. The continuum and the overall shape of the lines are very much the same as the one at high redshift. And one may wonder, why? Why is the case? Well, narrow line Seifert ones are different. So to be honest, she was very keen on the narrow line Seifert
No, yes,
one
just because from the X-ray point of view, the spectra, the continuum, or at least the things that you can resolve at high redshift looks very similar. Spectral shape that are steep, high accretion, the presence of outflows, jet, very strong, also in the radio band maybe. And
so, okay, I've got it. There is no indication that narrow line Seifert ones, on average, have a higher percentage of jets. There are radioactive narrow line Seifert ones, but some of them are selected because they were searched for. Optically speaking, the narrow line Seifert ones do have some clear signatures that have been used in order to identify them. One is the clear presence of strong iron blended lines. Those might be either indications, since the first paper that posed the point, those could be either the consequence of the fact that the accretion rate is close to Eddington, or that the inclination of the Brodmann region is close to Fison. But it doesn't seem to me that this would be the case for the high redshift systems.
To be honest, I have not looked at all the JWST spectrum because we do not have an handle on the optical ion complexes, only the UV ones.
But that's interesting. I mean, that's why I raised the point, because I mean, looks like maybe it can also be, again, a selection effect, because we are looking at them because of the high luminosity, and so we are picking just the one that show this. No.
Anything you want to raise again. This is gonna be, I guess, the research path for for the future. So I'm not sure. And
Actually, I just have a question for people here, and also it's because I'm not expertise about high redshift agents, because to my knowledge, I only know which is a kind of outflow called broad absorption line. It only happens in the quasars, which is high redshift agent, and I haven't saw this kind of outflows in the nearby agents. Can someone give me an answer, or is there any underlying physics mechanisms to explain this? I mean, why we only observe BAL, which is ball quasars,
Just at high redshift.
and why high redshift will cause that?
well, you can comment on this. So for me, BALs. So if we are talking about BALs, traditionally BALs were defined as such based on the carbon-4. So if you do see strong absorption, so I'm not sure if you ever seen like a spectrum of a strong BAL, that continuum is completely heated by, I don't know, strong absorption trough. Carbon-4 has broad absorption features, and this is what will define BALs. Then the definition has been changed, like there are mostly based still on carbon-4, but now there are other definitions based on I think carbon-3 or
Carbon-3.
And another one that uses still, I guess, carbon-3. But if you think about that, only these two emission lines have been used, then by definition these are observed in Sloan at redshift higher than 2. So low redshift BAL are at the moment, I'm not sure how they are defined. Not surely based on carbon-4, because it's not observed. So for me, it's a sort of selection effect.
Yes.
Unless you don't see like broad absorption features. Not sure if you want to comment on this or not. This would be my answer.
No, yes, I think it's the same. It's just that you observe them in that wavelength, so it's a selection effect, I would say. Yeah.
So one of the other points that I would like to mention, I don't know if you want to discuss this, but I very much like the Lisatina synergy. It's like something that has been occurring through, especially yesterday. That and I think this would be true at any given redshift, even a high redshift. So this is something that should be like in our mind.
stressed out more.
Stressed out by, yeah, all of us. That one single mission is hard to work, and then there would be like the famous word multi-messengers. We have been flooded by this multi-messenger word recently. You can like it or not, but it is actually what is happening. Anything more? You as young researchers, when you go back to your office, do you sometimes think what is the most pressing scientific question that you want to answer with your research? Or no, I have to do this piece of code today, and I want to know why this is crashing at this single line. Do you actually have you always think about the broad view, or thinking of the way to fly to Stockholm? I don't know. What would be? No, yeah, you can buy a ticket, but I'm saying when you invited you. From the theoretical perspective, what would be the main scientific question that you think, oh, this is such a neat result that I want to have? You don't have to answer. You can answer yourself and then send me when you have it. No, you have to answer right now. It works. Yeah. ChatGPT. Yeah. If I were.
I would never reply this kind of question with ask ChatGPT.
At least from my point of view, that all the theory, like including Eddington theory or Bodney theory or Shakura-Sunyaev, the Novikov-Thor models, they all have assumptions. Like they might look like, I don't want to say pretend, but they might look like we're doing something more sophisticated, but even these relativistic models, they solve the Kerr-metric in vacuum. So you solve something for the orbits of the accretion disk where you don't have any mass around the black hole, right? And all the orbits are equatorial orbits. If you go with tilted orbits with respect to the black hole, at least I don't know any solutions about that. So we have tilted disks in involve them with solutions that have the assumptions that the disk is perpendicular to the spin of the black hole. So there are a lot of assumptions that go in all of these models. So what I'm thinking personally is how we can use the theoretical tools you have, like simulations and codes, and try to move away from models with assumptions, kind of try and make our code faster. So I don't mean solve a whole galaxy using GR radiation MHD simulations, because that probably will never run. But if he said one. Yeah. When when are you planning on? Tomorrow. Tomorrow is Saturday. Yeah. Yeah, there are a lot of assumptions and there are a lot of limitation from like even the hardware, like taking one of these simulations and giving it to someone else with same ICs but different machine. The product will be different. Changing a random seed, like without changing any of the physics, the end galaxy will be different. Going to redshift 20 and moving a few particles away and running a cosmological simulation, redshift 0, the galaxy will be different. So there's a lot of numerical noise that propagates along with all the noise that comes from the free parameters that we use, like changing the value of pi will give you a different galaxy. So at least that's what I'm like, I'm more worried and thinking about how we can move, and it's also tied to the discussion yesterday about the subgrid modeling and how many models, and when do you stop adding models? You're actually improving your simulation, or just the complexity grows and it's harder to debug and understand what the code is doing. And I mean, probably not the most positive guy to ask what he thinks about, but at least that's what's how it's in my mind. Okay.
What is the main question that young astronomers would wonder? Yeah, I didn't have anything so wise to be recorded in YouTube, so that's why. But my point is that if the question is what a young astronomer would think about that day, would he think just to get the ticket for the airplane or to make his code run faster? The answer, I think that even if maybe it is pessimistic, you said, it is obviously let's make our code run faster, because now it is important to have large collaborations, and maybe you just make a very small step toward something I mean, important, and that's something that, I mean, you're lucky if you can do something like this, or for the rest, you just make a lot of assumptions, and maybe you can do something. So this is what I think. Tell me, please.
But do you want to win the Nobel Prize in informatics? That's what you want to in coding.
I would, but there is none. That's why.
Then
that will be my excuse then.
Do you have any feeling of which assumption, if dropped, would change the results the most? Or you have absolutely no idea, and all the point is give me more resources, because it's difficult to get resources, but it can be easier for these simulations. So do you have any feeling about which is the assumption that if dropped would change the result the most? Or to understand this, you still need more computer resources?
I mean, we've been talking a lot about black holes and how they grow. We have no idea, like, how we seed them. In the simulations, we just put them in to match with observations, but there could be a lot, like, I find that assumption, it's a very big assumption, and it has a lot of uncertainty, and we spend a lot of time making these very, very detailed models and you know, making them more and more complex. And obviously, like, we do understand things with those, but we have this crazy assumption where we just get to some mass limit and just pop a black hole in there and then watch how it evolves. And we even pin them to the center because we can't resolve dynamical friction a lot of the time in these cosmological simulations. Like, that assumption is probably, it has like some very big consequences. So I think like a lot of people, like some of the observers I know throughout the past 3 days have been saying like, we want some theoretical, you know, like we want something from the theory, like what if we see this result, what does it come from? Like, most of the stuff is also informed by some very basic relations that we also get from observations, right? Like, we just put a black hole seed in. So I think that the main thing of all of this, like, I think the high redshift observations now are extremely exciting. But like when we had this plot, right, where you can see the black hole growth and there's all of these different seeding mechanisms, like there's a lot of space. And I'm not sure, like I should know my like observations better and like seeding mechanisms, but like I don't actually know how well that will ever really be able to be constrained, because a lot of the theories work now, and I think all of our simulations are based on, like, for this particular topic, right, we all talk about AGN and things like this, like, I think that's a massive assumption, to come back to your question. Like, I think that's the main assumption, and we move on from that and then get these very complex models, but we actually have no idea what the seeding mechanisms is, and I think that that will like change a lot of things once we know more about it. And like you were saying about like the spin, like everything gets erased by the time we observe anything. Like, yeah, again, it's a bit pessimistic, but I don't know if we will ever know how they're seeded. Maybe somebody who knows more about black hole seeding wants to add to that. But
you're absolutely right, and it's worse than that in principle. If we do believe in some even short super-red internal accretion events that, by the way, are involved in the direct collapse scenario, because the direct collapse scenario at the beginning has a super-red internal accretion event, as well as the collapse of the POP3 star or a quasi-star. Is it the quasi-star, the one from Bigelman? Is that the name? Yeah, the quasi-star is super-red internal accreting, and if you allow for a super-red internal accretion event, then even the mass of the seed is erased. That is even better, right? So that what has to be proven. So when they will provide us with a supermassive black hole of 10 to the 10 solar masses, for which we have no doubt at redshift 20, we will be pretty sure that it is of cosmological origin, and we are fine. No, but now I'm joking. Now of course I'm joking. But it's, yeah, it is. If you allow for super-red internal accretion, it gets worse than that. You get less constraints on the other ingredient that in principle would change things is the feedback, the quasar feedback mode, to be more specific, for galaxy formation, because to me, it is pretty obvious that if whenever you release a huge amount of power, you will have outflows. It is undeniable, and you cannot prevent it. It doesn't need to have a strong impact on the galaxy. As a matter of fact, many times when we say there is such mass outflows associated with winds, and you integrate it in time, and you say it will quench the galaxy, in some cases the galaxy would be quenched before by star formation itself. And we are forgetting the fact that there will be new gas coming down from cosmological scales. So what if, for example, quasar mode AGN is not, quasar mode feedback is not the reason why we do not see too many supermassive black holes at high masses, and there's something else? But if it is not the case for the quenching of massive galaxies, as for other proposals that have been put forward, that this is an information that we plug in by hand in our simulations, and we are, at least I'm not completely sure about it. Because the radio feedback prescription, it seems to me that, yeah, but has implications for things that are in a pressurized system, like the central dominance of a cluster, for which we have some clear observational constraints. Maybe it's unclear how you transfer the energy. We had a talk, but at the very least, you see something, right?
If I can add something on black hole seeding, I mean, we can work on statistics at least to have some clues on that. But the point is that at higher redshift, where you have still some chances to find the systems with some information on their original nature, having large statistics, it seems to be very difficult. So that's why we hope in the next few years we have some better way to detect very faint AGN hosts, and from that maybe on average you can say something on the overall statistic, but then from that it's difficult to extrapolate some information for the very extremely massive ones, while you probably never know. I mean, but you will expect at that point a much higher number density with respect, for instance, as direct collapse black holes, but you can have it like primordial black holes, and you cannot, disentangle that from a lot of POP3 stars. I mean, probably. Yeah, they are lucky, and they grow efficiently.
Yeah, I wanted to comment exactly the same topic and agree, and I think there is something that we can learn about the seeds. Like we can look at low mass halos where we expect certain mechanisms to not be so important. We can try to figure out the population of wandering black holes and things like this. There is some hope, and I also wanted to emphasize on the fact that maybe the largest black holes that we see now at high redshift are not even the black holes that cause the trouble, because we can maybe grow a few of them, right? But if you, for example, believe studies that Thiago Costa has done, where he looked at the environments and tried to figure out what maybe the more pressing issues are, it's maybe even more difficult to get a population of black holes, like a vast population of black holes that is not as massive as the tip of the iceberg, but slightly below that. And I think we are not even sure what the actual issue is that we need to discuss. Like, is it the most massive black holes? Do we have to figure out how to grow them, or do we have to produce a lot of quite high mass black holes? I don't know. It's like we need to figure out what the population is that we have to match in a simulation. That is, I think, crucial for cosmological boxes at least. Otherwise, you don't know what you need to match in observations.
Yeah, I agree. In fact, actually, it seems that there is a very surprisingly high number density of faint systems above redshift 5. There's a high number density of faint high redshift system above redshift 5, and this is interesting because, I mean, it's difficult to recover that just with standard assumption of direct collapse black holes. It starts to be, to be in tension with that. So from that, maybe if we have more observation from with JWC, we can have some clues. But then, as you were saying, I mean, there is still a lot of degeneracy on smaller seeding potential mechanisms.
Probably I should have asked this question earlier then. Right? Try to trigger the discussion, because I think it's become more lively now that we are about to close and go for coffee. So, if you still want a coffee, which I believe you want, and we can continue the discussion outside. But thank you all.
to go? Yeah. Okay. Okay. Yeah. So this year was my first YAGN conference that I've been to. I was also I don't know what the right term is, given the privilege to do the theory summary. Yeah, I think before I get going with that, first, obviously I want to say thank you to the SOC and the LOC for organising the event, and also for everyone who's participated and provided such great science that I can now summarise. There was a wide range of topics covered this week, a number of which I'm definitely far from an expert in. So I may say things that aren't entirely correct, and I've probably forgotten things, and I apologise if I have forgotten anything. Please correct me if I am talking nonsense about something that you've presented, just so that everyone else can at least get the right picture. Okay, so I'm going to start off with something familiar to me. This is a slide from the talk I gave back on Wednesday, really summarising, I guess, from my point of view, being interested in galaxy formation, why we need supermassive black holes. From the discussion that we had before, maybe we don't need them to do the galaxy stellar mass function. But of course, this summary doesn't really do justice to the things we've had this week and the wide range of topics and systems that we've studied. And of course, when I first decided to study black holes, it wasn't because I wanted to try and get the turnover in the galaxy stellar mass function right. It's because these are, really extreme objects that can help you probe all sorts of physics and really interesting processes. But I think the key questions here kind of still work for everything we've heard in terms of seeding, growing black holes and how they impact their environment. So starting at the beginning, and this is really, I think, all talks from today. We've heard from a few talks about these high redshift, very massive quasars that we now see with JWST. We've seen a range of works, for example, semi-analytical models with different seeding populations, trying to understand how you can grow these massive objects from Alessandro, and then just before the break, or before the discussion group, we had Jun Hyung with simulations of low mass black holes, and in these works illustrating that it can be quite difficult to grow these low mass black holes and detect them with JWST. There's also the question of where these black holes grow, whether these very massive ones are in the highest density regions within the early universe, and we heard from Tommaso that it's not AGN feedback that's doing this, it's the observational bias that's leading to this behavior, with the observations disagreeing about how many satellites you see around these high redshift systems. Yesterday we also heard a lot then about how you bring massive black holes together. We had various versions of this process in all sorts of styles on slides, going through the dynamical friction regime, when you have wide separation black holes after a merger, and then there's various different processes bringing you down to the gravitational wave regime. We can start with the first one in modeling dynamical friction. I think as has been mentioned a number of times now, capturing dynamical friction is clearly important for a number of reasons, but it's very difficult in cosmological simulations simply because of the poor resolution, particularly for low mass black holes. But we've seen, for example, work from Ati here, including the Tremel dynamical friction model with Ketchu. Once you have high enough black hole masses, you can use it to integrate the dynamics locally to the black hole and the effects that this has on when mergers occur. Of course, it's not only dynamical friction acting on the black holes to bring them to the center, you also have dynamical friction acting on satellites that might merge in your system, and we had the talk from Ludovica yesterday as well, with this semi-analytic modeling of orbital decay and the inclusion of tidal stripping of satellites and the effect that this has on the rate at which the satellites move into the center of your galaxy. And of course, during this whole process, you have the potential for AGN on kiloparsec separations. It's your AGN. We've heard about observations of these things, and also Kunyang's talk with semi-analytic models trying to tell us what sort of systems are likely to host these kiloparsec scale dual AGN. And also, kind of on a similar topic here, with modeling dynamical friction, but also processes on smaller scales in gas-poor environments or massive ellipticals. We have had Nader's talk looking at what's, for his motivation, what's leading to core formation in massive ellipticals, and comparing scouring and gravitational wave recoil, finding in some systems scouring is sufficient, but in others you need these gravitational wave, these kicks from the gravitational wave recoil to lead to the core formation. The picture gets even messier when you've got your parsec or subparsec scale binary in gaseous environments. We had Chris's talk yesterday, and I also flashed up a few results from some simulations of circumbinary disks around circumbinary disks around binaries. As Chris highlighted, there's a whole range of different regimes of whether you have a self-gravitating disk or not, which seems to have important implications for whether the torques acting on the binary can help you shrink it or stall the shrinking. Differences in gas thermodynamics affecting this process as well as accretion onto the black hole. Chris presented new results looking also at precession of the binary and discussing implications for gravitational wave and EM signatures for these circumbinary systems. And I also presented some stuff looking at spin alignment from our subgrid accretion disk model and how things behave when you have misaligned or coplanar binaries. Of course, hand in hand with all of this, this multi-messenger term that maybe some people like more or less. And we had a couple of talks, one from David using semi-analytic modeling to try and identify what sort of hosts may have the massive black hole mergers and whether they're different from the standard population, and also looking for whether you can still detect the merger features to see if you can focus on particular galaxies where you might expect to see these mergers. And then the simulations from Qian using the obelisk simulations, looking at the potential electromagnetic signatures and whether binaries and mergers can be seen within the Lisa band, suggesting that some fraction of these could be observable in the X-ray and radio. But of course, the main problem with doing this is that I think both talks said this, that the Lisa localization is really challenging. Okay. We've also had a number of talks about AGN accretion and feedback, as you might expect. Earlier today, we had Dimitrios's overview of modeling a relativistic accretion disk in galaxy formation simulations. I think there are a number of works that have been trying to develop these more physically motivated subgrid accretion disk models where you can track the evolution of the accretion disk and the black hole spin. The work by Davide Fiacconi, and also new work by Sophie Kumani that's also in prep. And also coupling these models to, for example, jet feedback, such as the stuff that Rosie Talbot has done. And I also presented some stuff that's probably more traditional AGN feedback in massive systems and clusters, but that still has a number of unknowns in terms of how the energetics actually get to the ICM, given the difficulty in simulating high-resolution feedback in realistic environments. And then, again, in terms of modeling AGN accretion and accretion disk, we heard from Mazina trying to explain changing look AGN and how perhaps radiation pressure instabilities in accretion disks can give you changes in the accretion rate to explain these things. we also heard about nuclear star clusters and black holes in dwarf galaxies. Obviously, I think this idea of black holes and black hole feedback in low mass systems is somewhat newer, away from this traditional view for only needing the feedback in high mass systems. So both Jesse and Christian presented these very high resolution simulations of dwarf galaxies, not all isolated. Jesse's were looking at mergers as well, trying to understand the formation of nuclear star clusters. Jesse's showing that when you have these minor mergers, you can drive gas to the center and form the nuclear star clusters here. Christian was then adding black holes to these dwarf galaxies and highlighting how difficult it is to grow these black holes, particularly when you then include feedback and also the implications that this feedback will have on suppressing star formation in the center and preventing the formation of nuclear star clusters. I think they'll probably both agree with me, though, that also this work has a lot, there's a lot to do at high redshift and cosmological environments as well to be explored in this. Yeah, we also then heard from Antti. We heard that there's quite a few simulations employing Ketchu to capture the dynamics around the black holes, and Antti introduced the Bifrost code to us, this direct summation gravity solver with his list of requirements for a code here, and illustrating this by looking at eccentric stellar disks around a massive black hole, such as the one in the Milky Way, studying things like the eccentricity distribution, tidal disruption events, high velocity stars, and highlighting the importance of post-Newtonian effects, but also being, pointing out that you can still, it's still hard to match, both the kinematics and the stellar population within the Milky Way center. And then going all the way back to the first day, we had talks looking at TDEs, partial TDEs, MRIs, plunges. We had the first talk by Lisa pointing out the importance of modeling the loss cone correctly and partial TDEs, and how these might be able to explain differences between traditional predictions for TDE rates and the real TDE rate. We had Luca presenting models using their Fokker-Planck simulations to look at the rates of these events as a function of time, and highlighting that you can get different black hole growth times as a function of the black hole mass. We also had the model from Matteo trying to explain these quasi-periodic eruptions, assuming that you have some sort of Emery disk crossing, and as the object passes through the disk, it takes up this gas cloud, leading to the black body radiation and the formation of these eruptions, and comparing these to real observations, and then also highlighting some of the ongoing work running simulations of these things within Gizmo. Along similar lines, we also had the simulations from Changcheng looking at tidal peeling events. So here looking at low eccentricity systems to simulating a range of parameters. These are just a few examples up here. Finding that you can have accretion rates in these TPs that are super Eddington and potentially leading to ultra luminous transients. And then we had the talk from Adelia looking at jetted TDs. And I thought this was quite cool, combining different modeling, analytic models, and also taking from the GRMHD simulations and considering the different alignment timescales and different properties of the jet to explain different classes of these TDEs and the expected X-ray and radio observations. So I think that, that was a whirlwind tour through something of a random walk through the talks. I haven't got a list of profound conclusions. I think we've had lots of really good discussions. The one before the coffee break seemed to suggest that we only need to think about a few things like getting black hole dynamics, accretion, seeding, feedback, and then we'll be fine. But no, I think I'm nearly done. It's okay. But no, I think, yeah, we've seen lots of progress, lots of new models, new codes, lots, new subgrid models trying to include more physical processes, relying on higher resolution simulations to tell us what we should be putting into our lower resolution simulations. I think this can work both ways because you need the feedback onto the smaller scales as well. But yeah, I don't think I have too much else to say. So I'll stop there. I'll say thank you again to the organizers and everyone else that's been here to make it such a good few days. I'll stop there.
All right, so thank you very much for giving me the chance to give this summary talk. And as Martin said, I also hope I will cover briefly what we've talked about, and I hope everybody's contribution is well represented. If not, I'm really, really sorry, don't hate me. But first of all, round of applause for all the speakers in the observational side of things listed here. I think we had several great discussions and several new topics that I also was not too familiar with. So let's go through a few review of what everybody has talked about. First of all, we started with IXPE. IXPE is the first X-ray polarimeter that we have, and it's producing great results for us. So 2 to 8 kV, think if your sources emit in this range and if they can be polarized, do submit proposals. Well, next year, I guess. But what did IXPE did so far for us? Well, IXPE was great for revealing some of the most energetic processes in blazar jets. Again, blazars are these powerful jets pointed at us, but we really don't understand many things about them, and one of them is the acceleration processes in the jets. And finally, with the IXPE, we could get a glimpse as to what is happening and what is powering this acceleration into the jet of few objects, and it seems to be, at least the few sources that we studied, shocks. Shocks in the jet that maybe are also going through magnetic field lines and also changing the polarization. So this is the very first time we can actually tell two processes apart. And then we're also starting to understand maybe a bit of the geometry of the corona, because we know that there is a corona of electrons that is reprocessing the accretion disk radiation, emitting X-rays, but so far we usually like to portray it as just a blob of electrons on top of it. It seems to be thanks to polarization that actually we're more looking into these kind of scenarios where you have the accretion disk and then some slab parallel to the accretion disk, or maybe more of a wedge geometry. But again, forget the lamppost geometry, that's not right. We knew it, but now IXPE has confirmed it. And then we're starting to look into the dusty torus emission. So this dusty torus was supposedly this donut-shaped structure around the black hole. Now several observations are telling us that it's not really uniform. It's more patchy kind of distribution of dust and gas around the black hole. And IXPE is showing how polarized this emission is, informing us about the geometry and the distances of the tori from the center. So great results are gonna come up. Many people have submitted proposals like yesterday, so hopefully we're gonna learn new things from IXPE. Then another big question that has come up several times during these past few days is how do we measure black hole masses, and can we trust black hole mass measurements? And here Federica told us about how we can actually build a sample that is more unbiased towards obscuration, building a sample selected from the X-ray bus survey, and then you take a near-infrared spectra of them, and you get mass estimates. Turns out that these near-infrared mass estimates are very well in agreement with velocity dispatcher measurements and don't really depend on other factors, but what we need to do now is increase the redshift range for these black hole mass measurements, and therefore we really need, or she really needs, JWST, so give it to her if you are in the proposal panel. Again, to measure black hole masses, spectroscopy is not the only way, and Shelley-Ann has told us about how we could actually do this with ALMA and building velocity maps. So here are some of the images of the source she studied, and then they got ALMA data, and they will produce velocity maps that will actually inform us about the whole mass of the system, and therefore we can derive the central black hole mass. Of course, these kind of samples also need to be enlarged with more objects, but the ALMA resolution will really bring us to the central part of the source, informing us about the black hole mass. When we talk about AGNs, we also need to relate to the star-forming history of the system to maybe correlate the presence of an active nucleus to star formation history. And turns out that there is this very interesting class of objects, the so-called changing look AGN. Sometimes they have broad lines in their spectra, sometimes they don't. Why is this so? Apparently, they reside in a post-starburst galaxy. So the starburst phase has ended. And so what is the question that Margaret was trying to answer is what is happening in these systems, and mostly what is the star formation history of this system, and can we tell anything about the class of objects? And to do so, you need to collect very high resolution spectra and then apply models such as using Prospector to model it and inform us about the star formation history, which is now doable. And so we need to understand why there is this association with changing look AGN and quenching of the star formation. Then we switch on to day number 2, when a lot of people talked on the simulation side of mergers and mergers of AGN. From an observational point of view, we had a very nice talk by Marco, who informed us about this dual AGN in dwarf-dwarf mergers and how to find them. Apparently, X-rays are great to trace the accretion disk or the accretion onto these objects. So they selected 2 new candidates, dual AGNs in dwarf-dwarf mergers. Here's Mirabilis, one of them. And you see the optical image, then the X-rays where you distinguish the 2 sources, and then here overlap the different contours. Okay, so we see there is a mergers going on right here. And then they also looked into minor mergers, dual AGN, which are very rare. And here we have 1 other candidate, Swan and Odette. And then they're getting closer to get the first direct observation with JWST of hierarchical assembly, which I'm pretty sure you guys don't see. There is the contrast is not too high, but there is some tail and some structure right here. So stay tuned for new JWST results on these kind of sources. Going into dual AGN as well, Martina is trying to look at dual or lens AGN with Gaia data. So taking the Gaia database, they identify dual or lens AGN, and then follow up with an extensive optical and near-infrared campaign to obtain spectra of these sources and understand what is the system and what is happening. So here are some of the spectra and the images that they obtained through the campaign. And now finally, they have managed to resolve more than 15 kind of systems that are as a separation of 7 kiloparsec. Like right here, you see this plot. And before this work, this patch right here was absolutely empty. So we're starting to populate the plot in redshift and projected separation, getting closer and closer to this very close merger phase of the AGN. And now we move on into today, where we started talking about high redshift universe and how does it compare with the low redshift one. So Elisabetta told us about how quasar can be fantastic probes for cosmology and how can we use them. And because they can be used as standard candles, since the LX-LUV relation holds up to very high redshifts, they started working on to the Hubble diagram, which of course at low redshift right here, you see in very good agreement with the supernovae, and then you extend it to high redshift, and all of a sudden we have this discrepancy with the standard lambda CDM model. Is this real, or is this a bias by systematics? Well, all the systematic tests that they've done show that there is no bias, and this is something actually real that is happening, but we just need more sample size at the highest redshifts. And quasars are also interesting because we need to understand how long have they been there, what is their lifetime. And Silvia has showed us a variety of beautiful spectra of several quasars, and because of this dropout right here that you see at different wavelengths, we can actually understand the lifetime of the quasar using this RP value as a proxy. So we will be able to understand how long these quasars have been active for, and apparently at very high redshift, this seems to be very, very short time scale. And also we can start building average composite spectra for high redshift quasars, even beyond redshift 6. So this is great to see what's happening at the highest, in the earliest universe. Beyond redshift 6, we also have a lot of information thanks to X-rays. And as Alessia told us, we have found they have found extremely luminous, hyperluminous quasars with huge black hole masses. And if you trace back to their seeds, we see that the seeds are very, very massive as well. And so we need to start learning more about these sources. There seems to be a very good correlation with the photon index in X-rays and the mass of the seed. So there could be some correlation there to understand the coronal properties of the AGN itself, as well as the mass of the seed. However, need more time, and therefore a large XMM proposal. Again, if you're ever in the panel, please push for this kind of program to understand the high redshift universe. And something that wasn't really a high redshift talk, but more of another very interesting aspect of AGN is ultra-fast outflows from these sources. So these kind of very fast winds that come from the very central part of the AGN itself. And it turns out, as Jeroen showed us, that some of them seem to have lower, there is a relationship with the velocity and the Eddington accretion rate. So it seems as these winds actually slow down and they're pushed further away from the central supermassive black hole, depending on the accretion. So again, this comes the problem of accretion and how do these sources accrete and how they can produce these kind of winds. These I was not really familiar with this topic, but I found it very interesting. We talked a bit about my work on high redshift blazars, and we've confirmed that they peak at redshift beyond 4, so this connects them with supermassive black hole space densities, and they are the one that can actually contribute for most of the MEV background itself. And so what now we need is just to find more and more of these sources at higher redshift and probably have more X-ray instruments to find the furthest ones. Going back to the corona of the AGN at high redshifts, Elena is trying to look for high redshift through Nooster cycles, trying to find high redshift, very luminous sort of coronal AGN. And they found this very interesting source that they started putting here in the luminosity versus energy cutoff plot, trying to understand where these high luminosity sources fall in this diagram. And it seems to be that they are kind of above at least the limits, the theoretical limits. So we need to increase the sample size, and they do have more and more time with Nooster proposals to complete these kind of plots. So we look forward to see those results. And then JWST is going to help us pierce through the very early universe and try to understand what is the hierarchical building of our universe from the Big Bang up to the elliptical galaxies that we see today. And this was one of the first candidate system with JWST, a redshift 5 galaxy that shows signs that feedback could corroborate this scenario of the AGN feedback Hall star formation history. This was the talk by Elena. And then, yes, finally, just thank the SOC and the LOC with a round of applause for hosting us here. And that's it for me.
Thank you, Lea. Maybe before giving the last our coffee and lunch breaks. We already thanked Francesca that took care of this. Of course, now we want to thank Laura Lagatuta. She's in the direction, taking care, and she managed all the streaming process, and everything went fairly smooth. So Laura, this is for you. Perhaps Laura, you can come here if you can hear us. 1 second. Let's see. Oh, there is Laura. Thank you. We thank Giuseppe Fiasconaro, I think already left. He took care of the streaming on YouTube and logistic things. We thank Antonio Pagliaro and Giacomo Fazio for taking care of updating the websites and other things. And of course, we thanks the tour organizer, Pedro. Well, you asked me to do this, so I thank you for giving me the opportunity to do this thing. I was not aware of this meeting before, so I really appreciate. It was really a lot of fun, and I'm very glad for you who came here, the speakers, the moderators, all participants, and those also from online, in case you're still listening to us. And if you need more information about the rain that will come tonight and the train updates, just let me know. I'll give the final to the SOC.
So I think we already thanked everybody many times, but we still need to thank Ciro a lot for all his help. And see you all maybe next year. Ciao.